Hey guys, this is Jacob Sanders again, and today I'm going to be reading RFC 793, titled Transmission Control Protocol. This is going to be a really big one, so I'm going to have to break it into chunks, but I'm going to try and do a sizable amount today. And so let's just jump right into it. I'm going to skip over the table of contents and skip over the preface, get into here. Section 1, Introduction. The Transmission Control Protocol, or TCP, is intended for use as a highly reliable host-to-host protocol between hosts in packet-switched computer communication networks and in interconnected systems of such networks. This document describes the functions to be performed by the Transmission Control Protocol, the program that implements it, and its interface to programs or users that require its services. Section 1.1, Motivation. Computer communication systems are playing an increasingly important role in military, government, and civilian environments. This document focuses its attention primarily on military computer communication requirements, especially robustness in the presence of communication unreliability and availability in the presence of congestion. But many of these problems are found in the civilian and government sector as well. As strategic and tactical computer communication networks are developed and deployed, it is essential to provide means of interconnecting them and to provide standard inter-process communication protocols which can support a broad range of applications. In anticipation of the need for such standards, the Deputy Undersecretary of Defense for Research and Engineering has declared the Transmission Control Protocol, or TCP, described herein to be a basis for DoD-wide inter-process communication protocol standardization. TCP is a connection-oriented, end-to-end reliable protocol designed to fit into a layered hierarchy of protocols which support multi-network applications. The TCP provides for reliable inter-process communication between pairs of processes in host computers attached to distinct but interconnected computer communication networks. Very few assumptions are made as to the reliability of the communication protocols below the TCP layer. TCP assumes it can obtain a simple, potentially unreliable datagram surface from the lower level protocols. In principle, the TCP should be able to operate above a wide spectrum of communication systems, ranging from hardwired connections to packet-switched or circuit-switched networks. TCP is based on concepts first described by Cerf and Kahn in 1. The TCP fits into a layered protocol architecture just above a basic internet protocol, which provides a way for the TCP to send and receive variable length segments of information enclosed in internet datagram envelopes. The internet datagram provides a means for addressing source and destination TCPs in different networks. The Internet Protocol also deals with any fragmentation or reassembly of the TCP segments required to achieve transport and delivery through multiple networks and interconnecting gateways. The Internet Protocol also carries information on the precedence, security classification, and compartmentation of the TCP segments, so this information can be communicated end-to-end across multiple networks. Protocol layering. Higher level is above TCP, which is above Internet Protocol, which is above the communication network. Much of this document is written in the context of TCP implementations, which are co-resident with higher-level protocols in the host computer. Some computer systems will be connected to networks via front-end computers which house the TCP and Internet Protocol layers. Front-end computers which house the TCP and Internet Protocol layers, as well as network-specific software. The TCP specification describes an interface to the higher-level protocols, which appears to be implementable even for the front-end case, as long as a suitable host-to-front-end protocol is implemented. Section 1.2, Scope. The TCP is intended to provide a reliable process-to-process communication service in a multi-network environment. The TCP is intended to be a host-to-host protocol in common use in multiple networks. Section 1.3, About this document. This document represents a specification of the behavior required of any TCP implementation, both in its interactions with higher-level protocols and in its interactions with other TCPs. The rest of this section offers a very brief view of the protocol interfaces in operation. Section 2 summarizes the philosophical basis for the TCP design. Section 3 offers both a detailed description of the actions required of TCP when various events occur, such as the arrival of new segments, user calls, and errors, and the details of the formats of the TCP segments. Section 1.4, Interfaces. The TCP interfaces on one side to user or application processes, and on the other side to a lower level protocol such as the Internet Protocol. The interface between an application process and the TCP is illustrated in reasonable detail. This interface consists of a set of calls, much like the calls an operating system provides to an application process for manipulating files. For example, there are calls to open and close connections and to send and receive data on established connections. It is also expected that the TCP can asynchronously communicate with application programs. Although considerable freedom is permitted to let me just adjust here real quick. Okay, it is also expected that the TCP can asynchronously communicate with application programs, although considerable freedom is permitted to TCP implementers to design interfaces which are appropriate to a particular operating system environment. A minimum functionality is required at the TCP/user interface for any valid implementation. The interface between TCP and lower-level protocol is essentially unspecified, except that it is assumed there is a mechanism whereby the two levels can asynchronously pass information to each other. Typically, one expects the lower-level protocol to specify this interface. TCP is designed to work in a very general environment of interconnector networks. The lower-level protocol, which is assumed throughout this document, is the Internet Protocol. Section 1.5, Operation. As noted above, the primary purpose of the TCP is to provide reliable, securable logical circuit or connection service between pairs of processes. To provide this service on top of a less reliable internet communication system requires facilities in the following areas: basic data transfer, reliability, flow control, multiplexing, connections, precedence, and security. The basic operations of the TCP in each of these areas is described in the following paragraphs. Basic data transfer. The TCP is able to transfer a continuous stream of octets in each direction between its users by packaging some number of octets into segments for transmission through the internet system. In general, the TCPs decide when to block and forward data at their own convenience. Sometimes users need to be sure that all the data they have submitted to the TCP has been transmitted. For this purpose, a push function is defined. To assure that data submitted to a TCP is actually transmitted, the sending user indicates that it should be pushed through to the receiving user. A push causes the TCPs to promptly forward and deliver data up to that point to the receiver. The exact push point might not be visible to the receiving user, and the push function does not apply a record boundary marker. Reliability. The TCP must recover from data that is damaged, lost, duplicated, or delivered out of order by the internet communication system. This is achieved by assigning a sequence number to each octet transmitted and requiring a positive acknowledgment from the receiving TCP. If the ACK is not received within a timeout interval, the data is retransmitted. At the receiver, the sequence numbers are used to correctly order segments that may be received out of order and to eliminate duplicates. Damage is handled by adding a checksum to each segment transmitted, checking it at the receiver, and discarding damaged segments. As long as the TCPs continue to function properly and the internet system does not become completely partitioned, no transmission errors will affect the correct delivery of data. TCP recovers from internet communication system errors. Flow control. TCP provides a means for the receiver to govern the amount of data sent by the sender. This is achieved by returning a window with every ACK indicating a range of acceptable sequence numbers beyond the last segment successfully received. The window indicates an allowed number of octets that the sender may transmit before receiving further permission. Multiplexing. To allow for many processes within a single host to use TCP communication facilities simultaneously, the TCP provides a set of addresses or ports within each host. Concatenated with the network and host addresses from the internet communication layer, this forms a socket. A pair of sockets uniquely identifies each connection. That is, a socket may be simultaneously used in multiple connections. The binding of ports to processes is handled independently by each host. However, it proves useful to attach frequently used processes, e.g. a logger or time-sharing service to fixed sockets which are made known to the public. These services can then be accessed through the known addresses. Establishing and learning the port addresses of other processes may involve more dynamic mechanisms. Connections. The reliability and flow control mechanisms described above require that TCPs initialize and maintain certain status information for each data stream. The combination of this information, including sockets, sequence numbers, and window sizes, is called a connection. Each connection is uniquely specified by a pair of sockets identifying its two sides. When two processes wish to communicate, their TCPs must first establish a connection, initialize the status information on each side. When their communication is complete, the connection is terminated or closed to free the resources for other uses. Since connections must be established between unreliable hosts and over the unreliable internet communication system, a handshake mechanism with clock-based sequence numbers is used to avoid erroneous initialization of connections. Precedence and security. The users of TCP may indicate the security and precedence of their communication. Provision is made for default values to be used when these features are not needed. Section 2. Philosophy. Section 2.1. Elements of the internetwork system. The internetwork environment consists of hosts connected to networks which are in turn interconnected via gateways. It is assumed here that the networks may be either local networks, e.g. the Ethernet, or large networks, e.g. the ARPANET, but in any case are based on packet switching technology. The active agents that produce and consume messages are processes. Various levels of protocols in the networks, the gateways, and the hosts support an inter-process communication system that provides two-way data flow on logical connections between process ports. The term packet is used generically here to mean the data of one transaction between a host and its network. The format of data blocks exchanged within the network will generally not be of concern to us. Hosts are computers attached to a network, and from the communication network's point of view, are the sources and destinations of packets. Processes are viewed as active elements in host computers, in accordance with the fairly common definition of a process as a program in execution. Even terminals and files or other I/O devices are viewed as inter-process communication. Since a process may need to distinguish among several communication streams between itself and another process or processes, we imagine that each process may have a number of ports through which it communicates with the ports of other processes. Section 2.2. Model of operation. Processes transmit data by calling on the TCP and passing buffers of data as arguments. The TCP packages the data from these buffers into segments and calls on the internet module to transmit each segment to the destination TCP. The receiving TCP places the data from a segment into the receiving user's buffer and notifies the receiving user. The TCPs include control information in the segments, which they use to ensure reliable ordered data transmission. The model of internet communication is that there is an internet protocol module associated with each TCP which provides an interface to the local network. This internet module packages TCP segments inside internet datagrams and routes these datagrams to a destination internet module or intermediate gateway. To transmit the datagram to the local network, it is embedded in a local network packet. The packet switches may perform further packaging, fragmentation, or other operations to achieve the delivery of the local packet to the destination internet module. At a gateway between networks, the internet datagram is unwrapped from its local packet and examined to determine through which network the internet datagram should travel next. The internet datagram is then wrapped in a local packet suitable to the next network and routed to the next gateway or to the final destination. A gateway is permitted to break up an internet datagram into smaller internet datagram fragments if this is necessary for transmission through to the next network. To do this, the gateway produces a set of internet datagrams, each carrying a fragment. Fragments may be further broken into smaller fragments at subsequent gateways. The internet datagram fragment format is designed so that the destination internet module can reassemble fragments into internet datagrams. A destination internet module unwraps the segment from the datagram after reassembling the datagram if necessary and passes it to the destination TCP. The simple model of the operation glosses over many details. One important feature is that the type of service. This provides information to the gateway or internet module to guide it in selecting the service parameters to be used in traversing the next network. Included in the type of service information is the precedence of the datagram. Datagrams may also carry security information to permit hosting gateways that operate in multi-level secure environments to properly segregate datagrams from security considerations. Section 2.3, the host environment. The TCP is assumed to be a module in an operating system. The users access the TCP much like they would access the file system. The TCP may call on other operating system functions, for example, to manage data structures. The actual interface to the network is assumed to be controlled by a device driver module. The TCP does not call on the network device driver directly, but rather calls on the Internet Datagram Protocol module, which may in turn call on the device driver. The mechanisms of TCP do not preclude implementation of the TCP in a front-end processor. However, in such an implementation, a host to front-end protocol must provide the functionality to support the type of TCP user interface described in this document. Section 2.4, Interfaces. The TCP/user interface provides for calls made by the user on the TCP to open or close a connection, to send and receive data, or to obtain status about a connection. These calls are like other calls from user programs on the operating system. For example, the calls to open, read from, and close a file. The TCP Internet Interface provides calls to send and receive datagrams addressed to the TCP modules and hosts anywhere in the Internet system. These calls have parameters for passing the address, type of service, precedence, security, and other control information. Section 2.5, Relation to other protocols. The following diagram illustrates the place of the TCP in the protocol hierarchy. Here we see Telnet, FTP, and Voice as the application level, TCP and RTP as the host level, Internet Protocol and ICMP as the gateway level, and Local Network Protocol as the network level. It is expected that the TCP will be able to support higher level protocols efficiently. It should be easy to interface higher level protocols like ARPANET, Telnet, or AutoDIN to THP to the TCP. Section 2.6, Reliable Communication. A stream of data sent on a TCP connection is delivered reliably and in order at the destination. Transmission is made reliable via the use of sequence numbers and acknowledgments. Conceptually, each octet of data is assigned a sequence number. The sequence number of the first octet of data in a segment is transmitted with that segment and is called the segment sequence number. Segments also carry an acknowledgment number, which is the sequence number of the next expected data octet of transmissions in the reverse direction. When the TCP transmits a segment containing data, it puts a copy on a retransmission queue and starts a timer. When the acknowledgement for that data is received, the segment is deleted from that queue. If the acknowledgement is not received before the timer runs out, the segment is retransmitted. An acknowledgement by TCP does not guarantee that the data has been delivered to the end user, but only that the receiving TCP has taken the responsibility to do so. So it's like really pretty basic. You basically assume that nothing made it there until you get an acknowledgement back, and the acknowledgements are basically counting the amount of bytes and the order of those bytes. And the way the program works at the module level is you basically send the data you basically send the data you need to through TCP, and until you get the acknowledgement, it's stored in this retransmission buffer or queue, and it's associated with a timer, and if basically you pass by the timer's value, if the timer goes off, then you basically just retransmit and you repeat that indefinitely. And on the other side, the TCP receiver is basically waiting for the complete sequence of bytes to be there so that I can order everything correctly. And that is at least a large part of how the system works. So an acknowledgement by TCP does not guarantee that the data has been delivered to the end user, but only that the receiving TCP has taken the responsibility to do so. To govern the flow of data between TCPs, a flow control mechanism is employed. The receiving TCP reports a window to the sending TCP. This window specifies the number of octets, starting with the acknowledgement number, that the receiving TCP is currently prepared to receive. Okay. Section 2.7, Connection Establishment and Clearing. To identify the separate data streams that a TCP may handle, the TCP provides a port identifier. Since port identifiers are selected independently by each TCP, they might not be unique. To provide for unique addresses within each TCP, we concatenate an internet address identifying the TCP with a port identifier to create a socket, which will be unique throughout all networks connected together. Yeah, that makes sense. So basically, you have the source address, you have the destination address, you have the protocol, which is TCP, and then you have the port. And you probably have the port on the source as well, because, basically the idea is if I have a server and you have a computer that wants to connect to it, your computer might establish multiple connections, and the ports that your computer uses to connect are going to probably just be random ones, but there's going to be multiple different ones. And to differentiate between all of those different connections, it's going to use your source address plus your port plus my destination address plus my port plus the protocol, which is TCP. And when you combine all of that together, you'll have a unique identifier. Okay. To provide for unique addresses within each TCP, we concatenate an internet address identifying the TCP with a port identifier to create a socket which will be unique throughout all networks connected together. A connection is fully specified by the pair of sockets at the ends. A local socket may participate in many connections to different foreign sockets. A connection can be used to carry data in both directions. That is, it is full duplex. TCPs are free to associate ports with processes however they choose. However, several basic concepts are necessary in any implementation. There must be well-known sockets which the TCP associates only with the appropriate processes by some means. We envision that processes may own ports and that processes can initiate connections only on the ports they own. The means for implementing ownership is a local issue, but we envision a request port user command or a method of uniquely allocating a group of ports to a given process, e.g. By associating the high order bits of a port name with a given process. A connection is specified in the open call by the local port and foreign socket arguments. In return, the TCP supplies a short local connection name by which the user refers to the connection in subsequent calls. There are several things that must be remembered about a connection. To store this information, we imagine that there is a data structure called a transmission control block. One implementation strategy would have the local connection name be a pointer to the TCP for this connection. The open call also specifies whether the connection establishment is to be actively pursued or to be passively waited for. A passive open request means that the process wants to accept incoming connection requests rather than attempting to initiate a connection. Often the process requesting a passive open will accept a connection request from any caller. In this case, a foreign socket of all zeros is used to denote an unspecified socket. Unspecified foreign sockets are allowed only on passive opens. A service process that wished to provide services for unknown other processes would issue a passive open request with an unspecified foreign socket. Then a connection could be made with any process that requested a connection to this local socket. It would help if this local socket were known to be associated with the service. Well-known sockets are a convenient mechanism for a priori associating a socket address with a standard service. For instance, the telnet server process is permanently assigned to a particular socket, and other sockets are reserved for file transfer, remote job, entry, text generator, echoer, and sync processes, the last three being for test purposes. A socket address may be reserved for access to a lookup service which would return the specific socket at which a newly created service would be provided. The concept of a well-known socket is part of the TCP specification, but the assignment of sockets to services is outside the specification. Processes can issue passive opens and wait for matching active opens from other processes and can be informed by the TCP when connections have been established. Two processes which issue active opens to each other at the same time will be correctly connected. This flexibility is critical for the support of distributed computing in which components act asynchronously with respect to each other. There are two principal cases for matching the sockets in the local passive opens and a foreign active opens. In the first case, the local passive opens has fully specified the foreign socket. In this case, the match must be exact. In the second case, the local passive opens has left the foreign socket unspecified. In this case, any foreign socket is acceptable as long as the local sockets match. Other possibilities include partially restricted matches. If there are several pending passive opens recorded in the transmission control blocks with the same local socket, a foreign active open will be matched to a transmission control block with the specific foreign socket in the foreign active open. If such a transmission control block exists before selecting a transmission control block with an unspecified foreign socket. Yeah, I'm not really getting this exactly. What is it that's confusing about it? I think what's confusing about it is this passive opens versus active opens. I think I understand though, I'm just not 100% on it. I think a passive open is like basically when you set up a server and you're accepting connections. There's this concept when you program sockets that you set it into an accept mode. But then there's this other state which is like you, with the socket, you connect with it or you open it or something. I probably need to review all of the socket states and functions because it has something to do with this and I'm kind of missing that. Alright, well, let's just continue on. I think I'm here. The procedure to establish connections utilizes the synchronize control flag and involves an exchange of 3 messages. This exchange has been termed a 3-way handshake. Okay, a connection is initiated by the rendezvous of an arriving segment containing a SYN and a waiting TCP and a waiting transmission control block entry, each created by a user open command. The matching of local and foreign sockets determines when a connection has been initiated. The matching of local and foreign sockets. Yeah, I'm not completely sure what this local and foreign socket means. Also, a long time ago, earlier in this reading, I remember seeing it say that they were duplex. I'm not sure what that meant. I mean, I know what it means in general, that you can like send and receive through something, but it's not concrete in my mind. Anyways, moving on. The clearing of a connection also involves the exchange of segments, in this case carrying the FIN control flag. Okay, section 2.8, data communication. The data that flows on a connection may be thought of as a stream of octets. That makes sense to me. The sending user indicates in each send call whether the data in that call and any preceding calls should be immediately pushed through the receiving user by setting of the push flag. That also makes sense to me. A sending TCP is allowed to collect data from the sending user and to send that data in segments at its own convenience until the push function is signaled. Then it must send all unsent data. That makes sense to me as well. When a receiving TCP sees the push flag, it must not wait for more data from the sending TCP before passing the data to the receiving process. Okay, I got a little bit confused here. Let me read from here again. A sending TCP is allowed to collect data. I get confused a little bit when it goes sending TCP and receiving TCP. I understand that that's the client and the server, or that form the connection, but I need to, let me read through this again. A sending TCP is allowed to collect data from the sending user and to send that data in segments at its own convenience. I get that. That's like it's buffering it and it's sending it a little bit whenever it's like most efficient to send it. Unless you send the push like signal, that makes sense. That gives the user the ability to force it to flush the buffer, right? But when a receiving TCP sees the push flag, It must not wait for more data from the sending TCP. Okay, see, it makes sense to me now. So in the normal case, the TCP on your client connection is going to wait until it's going to wait. It's not going to send it immediately. But if you send the push bit, it's going to send it immediately. But the reason it's waiting a lot of the time is because it's waiting for more data from the sending TCP or from the server's TCP. And it's waiting for that before passing the data to the receiving process. It's still not super clear, but I'm going to move on. There is no necessary relationship between push functions and segment boundaries. Sort of. The data in any particular segment may be the result of a signal of a single SYN call in whole or part, or of multiple SYN calls. Okay. I'm going to go with, if I feel really like I understand something really well, I'm going to say the number 2. If I feel like 50-50 with it, I'm going to put 1. And if I feel like pretty confused, I'm going to put 0. And I'm just going to read a sentence and then say that. The purpose of the push function and the push flag is to push data through from the sending user to the receiving user. 2. It does not provide a record service. 0. I don't know what a record service is, what that has to do with that. There is a coupling between the push function and the use of buffers of data that cross the TCP user interface. 1. Each time a push flag is associated with data placed into the receiving user's buffer, the buffer is returned to the user for processing, even if the buffer is not filled. 1. If data arrives that fills the user's buffer before a push is seen, the data is passed to the user in buffer size units. 1. TCP also provides a means to communicate to the receiver of data. TCP also provides a means to communicate to the receiver of data that at some point further along in the data stream that the means to communicate to the receiver of data that at some point further along in the data stream than the receiver is currently reading there is urgent data. Okay, 2. TCP of pending urgent data. But the general notion is that the receiving process will take action to process the urgent data quickly. 2. Section 2.9, Precedence and Security. The TCP makes use of the Internet Protocol type of service field and security option to provide precedence and security on a per-connection basis to TCP users. 0. Not all TCP modules will necessarily function in all multi-level secure environment. Some may be limited to unclassified use only, and others may operate at only one security level and compartment. 1. Consequently, some TCP implementations and services to users may be limited to a subset of the multi-level secure case. Again, like 1. Like what do they mean by multi-level secure case and subset TCP implementations? I'm not sure what that is. Moving on. TCP modules which operate in a multi-level secure environment must properly mark outgoing segments with the security compartment higher level protocols such as Telnet or THP on interface to allow them to specify the desired security level compartment and precedence of connections. See, this is what's, I think, really, I understand that. I understand it now that I'd give that a 2. But what's confusing to me is we all use TCP every single day, but we never specify any of this stuff. All we do is throw in a port, a host, and that's it, pretty much. For the majority of these programs, like we write now, I mean, you have other things you throw in too sometimes, but what is this, desired security level, compartment, precedence? I mean, one thing I've heard of is TCP no delay. I think that might have to do with the push thing that we've just been talking about. reviewing, but still it's like not completely clear. 2.10 Robustness Principle. TCP implementations will follow a general principle of robustness. Be conservative in what you do, be liberal in what you accept from others. That was also said in the IP, or Internet Protocol RFC. This is going to be probably the part of this RFC that I understand better. Section 3, Functional Specification. Section 3.1, Header Format. TCP segments are sent as internet datagrams. 2. The Internet Protocol header carries several information fields, including the source and destination host addresses. 2. A TCP header follows the Internet header, supplying information specific to the TCP protocol. 2. This division allows for the existence of host-level protocols other than TCP. 1. I don't understand why this division allows for that exactly, but okay, the TCP header format. And then they have a 32-bit table. First 16 bits is the source port, second 16 bits is a destination port, next 32 bits is a sequence number, next 32 bits is an acknowledgement number, next 4 bits is a data offset, next 6 bits is reserved, and then the next six bits after that has the urgent, the ACK, the push, the RST, the SYN, and the FIN bits. The next 16 bits is the window, the next 16 bits is a checksum, the next 16 bits is the urgent pointer, the next 24 bits are the options, the next 8 bits are the padding, and after that you have data. Let's do it in bytes. The first 2 bytes are source port, the next 2 bytes are destination port, the next 4 bytes are sequence number, the next 4 bytes are ACK, and then the next 2 bytes have a data offset, reserved bits, and then urge, ACK, push, RST, SYN, and FIN bits in it. And then the next 2 bytes are the window, and then the next 2 bytes are the checksum, then the next 2 bytes are the urgent pointer, and then the next 3 bytes are options, and then the next byte is the padding, and then all bytes after that are data. I'd give that a 2. I understand that. The TCP header format, note that 1 tick mark represents 1 bit position. Alright, so the source port, it's 16 bits, it's the source port number. The destination port, it's 16 bits, it's a destination port number. The sequence number, it's 32 bits, the sequence number of the first data octet in this segment, except when SYN is present. Okay, the sequence number of the first data octet in this segment. 2. If SYN is present, the sequence number is the initial sequence number, and the first data octet is the initial sequence number plus 1. I think I'll give that a 1. I think I understand that, but if the acknowledgement number, it's 32 bits. If the ACK control bit is set, this field contains the value of the next sequence number the sender of the segment is expecting to receive. And this is where it gets really confusing about TCP, because there's like this overloaded thing where you're sending your data and all of the TCP header stuff, but when you're sending that, you're also actually in the same message that it's like in the same message, it's overloaded whether or not you're sending them like what you're what segment, what sequence number you're expecting next. Right? So all that information. So you're basically like telling them what to send you when you send what they told you to send too. It's like this really weird feedback, concurrent like, and it makes sense because it's more efficient, but it's somewhat misleading or more complicated because it's all sort of just shoved into one message. Okay, so if the ACK control bit is set, this field contains the value of the next sequence number the sender of the segment is expecting to receive. Once a connection is established, this is always sent. Right, and that makes sense. Basically, once you're connected, you're always acknowledging every single message you send to them has an acknowledgement number that's telling them what they need to send to you. And and you're keeping track of what you have that is, completely ordered and complete. Data offset, it's 4 bits. The number of 32-bit words in the TCP header. This indicates where the data begins. The TCP header, even one including options, is an integral number of 32 bits long. All right, this is something you see a lot of the time, and it can be confusing too. But this is a number, but its units are totally different. So this is the thing that isn't clear. And this is where ambiguity exists fundamentally in protocols and computer science. When you try and make something efficient, you have to assume information. And that information doesn't exist in the actual, it could be probably, how should I put it? It could be correlated after the fact without knowing about it, but it's actually just an assumption that's completely separate from the protocol itself. And so that's pretty much what all of these numbers are, is they have a unit associated with them. And so what this data offset is saying is this is a number that can be between 0 and 2 to the 4 is 16, I think. 1, 4, 0 and 15, or 1 and 16, right? But each one of those numbers actually is representing 32 bits or 4 bytes. And so, it could be 64 bytes. It could have been a 2-bit field, and it could have been 64-bit words, right? It could have been an 8-bit field and 16-bit words. But it's 4 bits and 32-bit words. I think some of that probably doesn't even matter if you change those things. Or it could just be 0 bits and always a certain length. Anyways, moving on. Reserved. This is 6 bits. It's reserved for future use. You see this in a lot of protocols. And then you have the control bits, which are 6 bits from left to right. The first is the urgent pointer field significant, the acknowledgement field, the push function, the reset the connection, synchronize sequence numbers, and then fin no more data from sender. This is related to the TCP state machine. The TCP state machine needs to flow in certain ways, and these things trigger different things in it. Like the push function makes TCP send things without buffering further. The acknowledgement field lets TCP know that it needs to take that number that it just received and use it to update all of its transmission control blocks so that they have the right, or I don't know if it's that, but so anyways, the window is 16 bits. This is a number. This is the number of data octets beginning with the 1 indicated in the acknowledgement field, which the sender of this segment is willing to accept. The number of data octets beginning with the 1 indicated in the acknowledgement field. Okay, so when you send a TCP message and you have an ACK, you have an ACK field set in your control bit, and then you have an acknowledgement number, and then you have a window. And the window is basically what you're willing to accept after the acknowledgement number, right? And so it allows the other side to send a bunch of different things at once, and then wait for you to basically acknowledge that they've been received. And you don't acknowledge every single thing. You acknowledge the chunks as you receive them, right? It's pretty miraculous that people got this going and it just works so well. Anyways, checksum is 16 bits. The checksum field is the 16-bit ones complement of the ones complement sum of all 16-bit words in the header and text. This is a super common pattern that you see everywhere. Basically, it's a way of trying to make sure that the data didn't get messed up in transmission. All it does is really decrease the probability of that. But the simple way of thinking about it is it's like you take this the 6-bit ones complement of the ones complement sum of all 16-bit words in the header and text. I think what that is basically you go through the entire segment 16 bits at a time and you XOR them together, and then whatever that value is stored in the checksum, or it is the 16-bit ones complement of that last thing, I believe. I'm not sure though, and I think the reason you do it that way is because if you do that on the receiving end, it's pretty easy to roll it out to make sure that you don't have any errors. And the way you do that is basically you just do the ones complement on the checksum again. You take that and ones complemented against each 16 bits in the segment. And if there's like, I think if the value is not 0, then you know it's incorrect. Or something. You know. But anyways, it's a way to make sure that something didn't go wrong in transmission. So if a segment contains an odd number of header and text octets to be checksummed, the last octet is padded on the right with zeros to form a 16-bit word for checksum purposes. The pad is not transmitted as part of the segment. While computing the checksum field itself is replaced with zeros. Yeah, that makes sense. The checksum also covers a 96-bit pseudo header conceptually prefixed to the TCP header. What? That's a 0. This pseudo header contains the source address, the destination address, the protocol, and the TCP length. This gives the TCP protection against misrouted segments. I understand both of those. Pseudo header. 96-bit. Okay, that's 32, 64. 96 is 3 of those rows. And where is that? I didn't see 0 PTCL and TCP length. This information is carried in the Internet Protocol and is transferred across the TCP network interface in the arguments of results of calls by TCP on the IP. The TCP length is the TCP header length plus the data length in octets. This is not an explicitly transmitted quantity, but is computed, and it does not count the 12 octets of the pseudo header. Alright, I'm going to give this a 1 for me. I kind of vaguely understand this, but not sure. The urgent pointer is 16 bits. That was all about the checksum. That's interesting. This field communicates the current value of the urgent pointer as a positive offset from the sequence number in this segment. Let me say that again. This field communicates the current value of the urgent pointer as a positive offset from the sequence number in this segment. Now I'll give that a 1. I couldn't. 1. This field is only to be interpreted in segments with the urge control bit set. That's a 2. You see, when you read text like this, it's like each sentence is different. Some are very easy to understand, others are quite difficult. I wonder what that is. I wonder why that is. It's probably like that for many people. It's probably more so just like some sentences just have more of an abstract like amount of information in them, whereas others are much simpler. I don't know. Options may occupy space at the end of the TCP header and are well, let's start with this. The options has a variable length, and the options may occupy space at the end of the TCP header. Okay, that's 2, and are a multiple of 8 bits in length. That's 2. All options are included in the checksum. That's 2. An option may begin on any octet boundary. That's 2. There are 2 cases for the format of an option. 2. Case 1, a single octet of option kind. 2. Case 2, an octet of option kind, an octet of option length, and the actual option data octets. Okay, so I've kind of recognized it for myself. An octet of option kind, 2, an octet of option length, 2, and the actual option data octets, 2. it's when you string too many things together, and like for my mind, you lose the context of all of them, and it just becomes sort of blurry. So the option length counts the 2 octets of option kind and option length, 2, as well as the option data octets. Okay, 2. Note that the list of options may be shorter than the data offset field might imply. 2. The content of the header beyond the end of option must be header padding, which is the value 0. 2. A TCP must implement all options. 2. Currently defined options include kind indicated in octal. 2. So the kind is 0, the length is hyphen, and the meaning is end of option list. The kind is 1, the length is hyphen, the meaning is no operation. The kind is 2, the length is 4, and the meaning is maximum segment size. I'd give that a 1. I'm not really sure. I kind of know what the point of this table is, but the meanings are not. I mean, yeah. Specific option definitions. The end of option list. The kind is 0, and then this is clear. It shows you all 8 bits. This option code indicates the end of the option list. 2. This might not coincide with the end of the TCP header according to the data offset field. 2. This is used at the end of all options, not the end of each option, and need only be used if the end of options would not otherwise coincide with the end of the TCP header. 1.5. No operation. Okay, that's a 2. This option code may be used between options, for example, to align the beginning of a subsequent option on a word boundary. 2. There is no guarantee that senders will use this option, so receivers must be prepared to process options even if they do not begin on a word boundary. 2. Maximum segment size, and it shows 4 bytes. Oh, I see. Okay. The table earlier makes more sense now. Its kind is the value 2, its length is 4, and then it has a max segment size. Maximum segment size option data is 16 bits. If this option is present, then it communicates the maximum received segment size at the TCP, which sends the segment. This field must only be sent in the initial condition request, i.e. in segments with the syn control bit set. If this option is not used, any segment size is allowed. Padding is a variable length. The TCP header padding is used to ensure that the TCP header ends and data begins on a 32-bit boundary. 2. The padding is composed of zeros. 2. Section 3.2, Terminology. Before we can discuss very much about the operation of the TCP, we need to introduce some detailed terminology. 2. The maintenance of a TCP connection requires the remembering of several variables. 2. We conceive of these variables being stored in a connection record called a transmission control block, or TCB. 2. Among the variables stored in the TCB are the local and remote socket numbers. 1. I'm not sure what those numbers are. I understand what a number is. I understand what local and remote and socket is. But are those like the IP addresses? Or are those something different like memory addresses? I don't know. The security and precedence of the connection. Yeah, let's go back here. Among the variables stored in the TCB are the security and precedence of the connection. 2. Pointers to the user's send and receive buffers. 2. That makes more sense now. That's why it's duplex, right? Because it has a receive buffer and a send buffer. Okay. Inside the TCB is also pointers to the retransmit queue and to the current segment. 2. In addition, several variables relating to the send and receive sequence numbers are stored in the TCP. 2. All right, send sequence variables. We have send unacknowledged, send next, send window, send urgent pointer, send sequence number used for the last window update, send acknowledgement number used for the last window update, and then initial send sequence number. And then the receive sequence variables are receive next, receive window, receive urgent pointer, and initial receive sequence number. I'm going to give that a 1. I'm not really sure what these variables are for exactly. I guess maybe it's saying those are the ones stored in TCP that lets you know like where you are in the state machine or something. The following diagrams may help relate some of these variables to the sequence space. Okay, that makes sense to me too. Send sequence space is made up of 4 different states. The first is old sequence numbers which have been acknowledged. The second is sequence numbers of unacknowledged data. The third is sequence numbers allowed for new data transmission for future sequence numbers which are not yet allowed. Oh, okay, I think I understand this. What it's saying is it's breaking up the send sequence space in terms of when you're sending data, you're sending a bunch of bytes, and when you are sending those bytes, you have bytes which have been acknowledged already, and then you have bytes which have not been acknowledged, and then you have bytes that are still allowed for new data transmission, and then you have bytes which are outside of the window and are not allowed. Sequence numbers of unacknowledged data, sequence numbers allowed for new data transmission. Okay, yeah, so the ones that have been acknowledged are good. The whole thing is done. The ones that have been unacknowledged, you sent, but you haven't received back. The ones that are good for new data transmission haven't even been sent, so they couldn't possibly be acknowledged. The ones which aren't even allowed to be sent are outside of the window, and this is called the send sequence space. All right, let's look at the receive sequence space. It's a little bit simpler, or at least it has less states or less partitions in the space. The first part is old sequence numbers which have been acknowledged. Okay. The second part is sequence numbers allowed for new reception. Okay, and the third is future sequence numbers which are not yet allowed. Okay. So when you're receiving data, you're going to communicate with the other side what you need to receive. And so the way it works is you're going to send them the last byte that has been completely acknowledged up to. And then you're going to have a window after that. And you're going to be accepting basically anything between that and the window. And okay. The receive window is the portion of the sequence space labeled 2 in figure 5. Yeah. There are also some variables used frequently in this discussion that take their values from the fields of the current segment. Current segment variables. The segment sequence number, okay. The segment acknowledgement number. The segment length, the segment window, the segment urgent pointer, and the segment precedence value. So the segment sequence number is what your data is, what you're sending to them. The segment acknowledgement number is what you've gotten from them. The segment length is how long the data is that you're sending. The segment window is, I think, also what data you are willing to receive after the acknowledgement. The segment urgent pointer is related to something I don't really get, and the segment precedence value is also related to something I don't really get. A connection progresses through a series of states during its lifetime. The states are listen, send sent, send received, established, fin wait 1, fin wait 2, close wait, closing, last act, time wait, and the fictional state closed. Closed is fictional because it represents the state when there is no TCP and therefore no connection. Briefly, the meanings of the states are, this is going to be interesting, listen, which represents waiting for a connection request from any remote TCP import. 2, I understand that. Send sent represents waiting for a matching connection request after having sent a connection request. I think this is on the client side. That's my guess, but since I'm not 100%, I'm going to go with 1. SYN received represents waiting for a confirming connection request acknowledgement after having both received and sent a connection request. This happens on the server side. The client sends the SYN sent, the server receives the SYN sent, and then it sends the SYN received. And then you have, that's my guess at least, I'm going to go with 1 on that as well. Established represents an open connection. Data received can be delivered to the user. The normal state for the data transfer phase of the connection. Okay, so client says, let's synchronize. Server says, we're synchronized. And now it's established, right? And I don't know if that's like its own message, but okay, so fin wait 1 represents waiting for a connection termination request from the remote TCP or an acknowledgement of the connection termination request previously sent. I'm going to go with 1, mostly because I'm not sure what an acknowledgement of the connection termination request previously sent. Does that mean that the server sent the termination request? That's what I'm going to assume. Fin wait 2 represents waiting for a connection termination request from the remote TCP. So I think basically it's like whichever one sends the connection termination request is basically the fin wait 1. It's just like I'm firing the fin wait 1, and then the other one's like, oh, I got a fin wait 1, and it sends the fin wait 2 to the other one. And then you enter close wait, and that represents waiting for a connection termination request from the local user. I'm not sure about that. I don't know what they mean by local user. Closing represents waiting for a connection termination request acknowledgement from the remote TCP. I don't get how that's different than fin wait 2 or okay, so I'm a little bit confused here. Last stack represents waiting for an acknowledgement of the connection termination request previously sent. Represents waiting for an acknowledgement of the connection termination request previously sent to the remote TCP, which includes an acknowledgement of its connection termination request. Time wait represents waiting for enough time to pass to be sure the remote TCP received the acknowledgement of its connection termination request. Yeah, I'll be honest. The confusing part is all of it. It's confusing because it's not so clear who's who, like what is the local user in close wait. What exactly is remote TCP? Is that just on either side? But okay, maybe if we read this lower, it'll make more sense. A TCP connection progresses from one state to another in response to events. The events are the user calls open, send, receive, and close. Close, abort, and status. The incoming segments, particularly those containing the SYN, ACK, RST, and FIN flags, and timeouts. 1. The state diagram in Figure 6 illustrates only state changes together with the causing events and resulting actions, but addresses neither error conditions nor actions which are not connected with state changes. In a later section, more detail is offered with respect to the reaction of the TCP to events. This diagram is only a summary and must not be taken as the total specification. Basically what they're saying there is it's incomplete, and they're saying it for this diagram down here. So we'll try and parse this, and then I'm probably going to take a break because it's been a while. See, I don't even know where you start here, I guess with listen. So listen, if you receive a SYN event, then you send a SYN ACK, and if a SYN is then a SYN is received, you receive an ACK of SYN. Like, how do you even read this? Passive open creates a TCB. Close. Okay, that is clear enough. Okay, so why is passive open next to the arrow pointing from closed to listen? Because it's going from closed to listen? Okay. This makes more sense. You start at closed. So all connections start in a closed state, I guess. And when you open it, when you do a passive open, you create a transmission control block. Then you're in the listen status. If you close while you're in the listen status, you delete the transmission control block. If you go from closed to the SYN sent state, it looks like you can, then that is an active open, and that is creating the transmission control block and sending a SYN. Yeah, okay, this is making a lot more sense. If you go from the SYN sent state to the closed state, then you close and you delete the transmission control block. So all connections start in the closed state. As a client, you do an active open where you send, first you create a TCB data structure, and then you send a SYN. Okay, that's the first step as a client. The first step as a server is you go from closed, you have a passive open, which just creates a transmission control block. From listen, you can send a SYN. You can send a SYN. Okay, listen can go. You can go from closed to listen, then you can go from listen to SYN sent, or you can go from listen to SYN received. Usually, it's probably going to be like, okay, so if you're a server, you're not going to send something at the beginning. You're probably going to receive a SYN from an active connection. So you'll go from the listen state to the SYN receive state, while they will have gone from the closed state to the SYN sent state. After you have reached the SYN receive state, if you're going to close the connection from the SYN receive state, you'll send the fin bit. If you're going to, okay. Okay. SYN sent. I think receive SYN, send ACK, send SYN ACK, send SYN. What it's trying to say, the arrows kind of make this a nightmare, but also help. So they'll listen when if you're a server and you have a passive open and then you receive a SYN packet, then you're going to send a SYN ACK. When you send a SYN ACK, I don't see an arrow for that. I don't see an arrow for that. So if you're an active, let's try from the client side. If you go from closed to SYN sent, and you basically create the TCB and then you send the SYN. There isn't an arrow in terms of sending the SYN, but I suppose what's so confusing about this is they're both merged on the same thing, and you want to interpret the arrows as being related to actions, but they're really just changes in state. And so it's like, this is the way it works. So you start enclosed, you create the TCP, you send the SYN, and then you're in the SYN state. The only way you change from this state is by receiving a SYN. And if you receive a SYN, then you go to the SYN received state. If you receive a SYN ACK, you go to the established state, and you send an ACK of your own. It's super confusing how they've done this, but maybe it's just impossible to kind of like show this in a way, right? So yeah, so in the listen state, you can go to the SYN sent state basically after you send a SYN. But you can go into the SYN received state after you receive a SYN. From the SYN received state, you can go to established by sending an if you receive the ACK of a SYN, it is established from SYN received. The only states from SYN received you can go to are established or close. Yeah, man, this is a nightmare. Some of it makes sense more easily than others. This middle section is so confusing, though. In the SYN sent state, if you receive a SYN, you go to the SYN received state and you send an ACK. In the listen state, if you receive a SYN, you go into SYN received. If you send something, then you go into SYN sent. There's the receive SYN ACK, and then there's the receive ACK of SYN. What? I think I finally have kind of seen this. So what happens is the client be in the state of SYN received, in which case it's going to send a SYN ACK back to the client. The client will receive the SYN ACK, which will then cause it to send the SYN ACK back to the server. The server in the SYN received state will receive the ACK of the SYN, which was what was just sent by that, and that will put it, both of them will be in the established state at that exact time. And then it will send X data from its server. They're both in the established state, so then basically there's two different states from established you can go into. One is close wait, and that's when you receive a fin, and the other is fin wait 1, which is when you receive a close. When you receive a fin, you respond with send ACK. When you receive a close, you respond with send fin. The way to interpret this weird line thing is basically the thing on the top is what happens to you, and the thing on the bottom is what you do to the other process on the other side. And so fin wait, if it receives a fin while you're in fin wait 1, then you'll send an ACK, which will put you in closing. If you're in fin wait and you receive an ACK of fin, then it'll put you in fin wait 2. And this is kind of weird. It says receive ACK of fin, then it says that you'll send X, which is the same as when you establish. Maybe the X means you won't send anything. I'm not really sure. Or maybe it means that you send an arbitrary amount of stuff. In any event, I'm going to stop here for a while. It's been a day or two, and I'm going to start reading. I'm going to pick up from where I was. I was reading RFC 793, which is on Transmission Control Protocol, or TCP. This is section 3.3, sequence numbers. A fundamental notion in the design is that every octet of data sent over a TCP connection has a sequence number. Since every octet is sequenced, each of them can be acknowledged. The acknowledgment mechanism employed is cumulative, so that an acknowledgment of sequence number X indicates that all octets up to, but not including X, have been received. This mechanism allows for straightforward duplicate detection in the presence of retransmission. Numbering of octets within a segment is that the first data octet immediately following the header is the lowest numbered, and the following octets are numbered consecutively. Yeah, okay, kind of a weird wording, but basically it's just what you'd expect. It is essential to remember that the actual sequence number space is finite, though very large. The space ranges from 0 to 2 to the 32 minus 1. Since the space is finite, all arithmetic dealing with sequence numbers must be performed modulo 232. This unsigned arithmetic preserves the relationships of sequence numbers as they cycle from 2 to the 32 minus 1 to 0 again. There are some subtleties to computer modulo arithmetic, so great care should be taken in programming the comparison of such values. The symbol less than or equal to means less than or equal to modulo 2 to the 32. The typical kinds of sequence number comparisons which the TCP must perform include A. Determining that an acknowledgement refers to some sequence number sent but not yet acknowledged. B. Determining that all sequence numbers occupied by a segment have been acknowledged, e.g. to remove the segment from a retransmission queue. C. Determining that an incoming segment contains sequence numbers which are expected, i.e. that the segment overlaps the receive window. Right, so you can imagine basically one of the TCP programs running receives some data, and the first thing they do is look at what the sequence number for that data is, and they use that sequence number to basically figure out if it's a duplicate, if it is within the window, or it's outside of the window. And then they figure out other things like how much of the data from like what value to the other value has been completely delivered, which I guess is how it detects duplication. In response to sending data, the TCP will receive acknowledgments. Yes, the following comparisons are needed to process the acknowledgments. 2. Also, if you're not familiar, after I read a sentence, a lot of the time I'll use a number. 0 meaning I didn't really understand it at all. 1 being I was fairly confused, but kind of get something about it. And then 2 being I understand most of it and I feel fairly confident with it. Alright, so the following comparisons are needed to process the acknowledgments. 2. Sin.una equals the oldest unacknowledged sequence number. Sin.next equals the next sequence number to be sent. Segment.ack equals the acknowledgement from the receiving TCP next sequence number expected by the receiving TCP. Segment.sec equals the first sequence number of a segment. Segment.length equals the number of octets occupied by the data in the segment, counting sin and fin. And then the segment.sec plus the segment.length minus 1 equals the last sequence number of a segment. A new acknowledgement called an acceptable act is one for which the inequality below holds. The oldest unacknowledged sequence number is less than the the acknowledgement from the receiving TCP. And that's also less than or equal to the next sequence number to be sent. So it's not crystallized in my mind, but basically this is going through the process of using the acknowledgement numbers you receive from the other TCP program. So it sends you the acknowledgement numbers, and you use those acknowledgement numbers to figure out your own, like, the next thing you're going to send, or what you're going to retransmit, or what you're, basically the acknowledgement they send to you has to do with the sequence number that you're about to send. Or that's in this example, it's the send.next, which is the next sequence number to be sent. A segment on the retransmission queue is fully acknowledged. I think the other thing to understand is that a segment, I think, might refer to many different, like, a segment is too large to send in a single message, I believe. And so TCP is like helping guarantee that. But the segment is, but I'm not sure about this. Anyways, a segment on the retransmission queue is fully acknowledged if the sum of its sequence number and length is less than or equal. If the sum of its sequence number and length, okay, that's a 2, is less than or equal than the acknowledgement value in the incoming segment. Right, okay. When data is received, the following comparisons are needed. 2. Receive.next equals the next sequence number expected on an incoming segment, segments, and is the left or lower edge of the receive window. Receive.next plus receive.wind minus 1 equals the last sequence number expected on an incoming segment and is the right or upper edge of the receive window. Segment.sec equals the first sequence number occupied by the incoming segment, and segment.sec plus segment.length minus 1 equals the last sequence number occupied by the incoming segment. A segment is judged to occupy a portion of valid receive sequence space if the segment, if within the segment the receive.next is less than or equal to the segment.sequence number, which is less than the receive.next plus receive.window. Interesting. Let's continue. I don't feel super confident about this, but I know high level what it's supposed to be doing. The first part of this test checks to see if the beginning of the segment falls in the window. The second part of the test checks to see if the end of the segment falls in the window. Okay. If the segment passes either part of the test, it contains data in the window. Right. Okay, so that makes sense. So basically, you can think of every single TCP message, or I guess a segment, is basically, it's got its TCP header, which has got all this information in it, and then it has the payload, which more or less the payload, you need it because you want to know how long it is. And so inside the TCP header, there is a sequence number, and then there's the length of the payload, which when you take the sequence number and add the length of the payload to it, you get basically the full chunk of data that is being represented there. And in order to make sure that when you send those messages over the unreliable internet that you never lose any of them and that they're reassembled in the correct order, what you have to do is make sure that you have every single byte from the beginning to the end. And so you basically know that you need to resend data or send it in the first place if any of the bytes within the range, which is from the sequence number to basically the sequence number plus the length of the payload, if any of those bytes haven't been acknowledged by the other side, you have to retransmit it, right? And that's how this basically works. Actually, it is a little more complicated than this due to 0 windows and 0 length segments. We have 4 cases for the acceptability of an incoming segment. So the first case, and they have here the segment receive, the segment length and the receive window, and then they have the test. So basically, if the segment length is 0 and the receive window is 0, then the segment sequence number equals the next sequence number expected on incoming segments. The other thing that you got to understand about TCP is it's a protocol that's juggling what you're supposed to be receiving, like in terms of incoming data, and also what you should be sending. Both sides are keeping track of what they've sent, what they need to send, what the other has received, and what the other needs to receive, right? And that's how it works out so well. Okay, so the first part of, okay, so yeah, we have this first test there, and then you have another case where the segment length is 0, but the receive window is greater than 0. And then you have a segment case where the segment length is greater than 0, but the receive window is 0. Then you have where both of those different things are greater than 0. And yeah, as I thought, if the segment length is greater than 0, but the receive window is less than 0, that just seems not acceptable, which is what they say. But if the receive window is greater than 0, then the sequence number, okay, let's read this again. The next sequence number expected on an incoming segment, it is the left lower edge of the receive window. So the left lower edge of the receive window has to be less than or equal to the current sequence number. Seg.sec is the first sequence number occupied by the incoming segment. Okay, so this is the incoming segment's sequence number. This was the left edge of the receive window. So yeah, basically, if this is greater than or equal to this, and then this plus, yeah, then that's one case. That's the test. And then there's this other case where basically this is greater than or equal to this, but less than this, or this plus the length. This is what I was saying, right? So, yeah, basically this seems like the main case that the whole algorithm runs on, which is if the incoming sequence number plus the length of the segment itself, if that falls within this window, which is between the left edge of the receive window and the right edge of the receive window, then it passes the test. Okay, let's continue. Note that when the receive window is 0, no segments should be acceptable except ACK segments. Why is this true? Because you acknowledge something in the TCP header itself, and so you can essentially, it's considered to be a segment of length 0 because all of that header information is referring to what's inside the payload, right? Obviously, the header still takes up data, but it's data that is like more or less not guaranteed to be sent, right? It's funny, but like the TCP header data is not being tracked. It's the payload data that's being tracked by the TCP header data, right? Thus, it is possible for a TCP to maintain a 0 receive window while transmitting data and receiving ACKs. However, that's kind of interesting. However, even when the receive window is 0, a TCP must process the RST and urge fields of all incoming segments. We have taken advantage of the numbering scheme to protect certain control information as well. This is achieved by implicitly including some control flags in the sequence space so that they can be retransmitted and acknowledged without confusion, i.e. one and only one copy of the control will be acted upon. Control information is not physically carried in the segment data space. Consequently, we must adopt rules for implicitly assigning sequence numbers to control. The SYN and FIN are the only controls requiring this protection, and these controls are used only at connection opening and closing. For sequence number purposes, the SYN is considered to occur before the first actual data octet of the segment in which it occurs, while the FIN is considered to occur after the last actual data octet in a segment in which it occurs. The segment length, or seg.length, includes both data and sequence space occupying controls. When a SYN is present, then the seg.sequence is the sequence number of the SYN. So I got a little bit confused there, but I grasped some of it. I'll give that section a 1. Initial sequence number selection. The protocol places no restrictions on a particular connection being used over and over again. 2. A connection is defined by a pair of sockets. 2. New instances of a connection. New instances of a connection will be referred to as incarnations of the connection. Let me read this again. New instances of a connection will be referred to as incarnations of the connection. I'll give that a 1. The problem that arises from this is, how does the TCP identify duplicate segments from previous incarnations of the connection? That actually makes a lot of sense to me too, because it's like mod. Yeah. This problem becomes apparent if the connection is being opened and closed in quick succession. Okay, 2, I get that. Or if the connection breaks with loss of memory and is then reestablished. Okay, true. To avoid confusion, we must prevent segments from one incarnation of a connection from being used while the same sequence numbers may still be present in the network from an earlier incarnation. That makes sense to me too. We want to assure this even if a TCP crashes and loses all knowledge of the sequence numbers it has been using. 2. When new connections are created, an initial sequence number, or ISN generator, is employed which selects a new 32-bit ISN. 2. The generator is bound to a possibly fictitious 32-bit clock whose low-order bit is incremented. The generator is bound to a possibly fictitious 32-bit clock whose low-order bit is incremented roughly every 4 microseconds. Thus, the ISN cycles approximately every 4.55 hours. Since we assume that segments will stay in the network no more than the maximum segment lifetime, and that the MSL is less than 4.55 hours, we can reasonably assume that ISNs will be unique. Okay, I'll give this a 1. For each connection, there is a SYN sequence number and a receive sequence number. 2. The initial SYN sequence number, or ISS, is chosen by the data sending TCP, and the initial receive sequence number, the IRS, is learned during the connection establishing procedure. 1. For a connection to be established or initialized, the two TCPs must synchronize on each other's initial sequence numbers. For a connection to be established or initialized, the two TCPs must synchronize. I'll give that a 1. This is done in an exchange of connection establishing segments carrying a control bit called SYN for synchronized and the initial sequence numbers. 1. As a shorthand, segments carrying the SYN bit are also called SYNs. Hence, the solution requires a suitable mechanism for picking an initial sequence number and a slightly involved handshake to exchange the initial sequence numbers, or ISNs. Give it a 1. The synchronization requires each side to send its own initial sequence number and to receive a confirmation of it in acknowledgement from the other side. Okay, each side must also receive the other side's initial sequence number and send a confirming acknowledgement. This makes sense to me. 2, I send the sequence number I'm starting with. You send an acknowledgement that you know what it is. Okay, and then they have an example of this. 1, A sends to B. Sends my sequence number is X, and then B sends back to A, acknowledge your sequence number is X. Then B has also sent, potentially in the same thing, my sequence number is Y, and then A sends back, I acknowledge your sequence number is Y. So it's a bit of an echo, right? You basically just echo, and once everyone knows that that's good, then they can proceed from there synchronized. Because steps 2 and 3 can be combined in a single message, this is called the 3-way handshake. That makes so much sense to me. I'll give that a 2. A 3-way handshake is necessary because sequence numbers are not tied to a global clock in the network, and TCPs may have different mechanisms for picking the ISNs. This also makes sense to me. Like, imagine we lived in a world where there was this special function you could call in any program that told you like exactly what the time was. Then it might not even really be necessary to have any of this information, because you could just put that information into like all of your messages and it would tell the other side with complete conviction that you were synchronized, right? But because that's not true, and time is like wildly like complicated and not necessarily synchronized and all sorts of other stuff, but instead you have to basically at the beginning synchronize two different programs. Okay, so right, a three-way handshake is necessary because the sequence numbers are not tied to a global clock in the network, and TCPs may have different mechanisms for picking ISNs. The receiver of the first SYN has no way of knowing whether the segment was an old delayed one or not, unless it remembers the last sequence number used on the connection, which is not always possible. And so it must ask the sender to verify this SYN. The three-way handshake and the advantages of a clock-driven scheme are discussed in section 3, or in this link. Knowing when to keep quiet. To be sure that a TCP does not create a segment that carries a sequence number which may be duplicated by an old segment remaining in the network, the TCP must keep quiet for a maximum segment lifetime before assigning any sequence numbers upon starting up, or recovering from a crash in which memory of sequence numbers in use was lost. For this specification, the MSL is taken to be 2 minutes. This is an engineering choice and may be changed if experience indicates it is desirable to do so. Note that if a TCP is reinitialized in some sense, yet retains its memory of sequence numbers in use, then it need not wait at all. It must only be sure to use sequence numbers larger than those recently used. Yeah, some of this makes sense. I'll give that a 1. The TCP quiet time concept. The specification provides that hosts which crash without retaining any knowledge of the last sequence numbers transmitted on each active connection shall delay emitting any TCP segments for at least the agreed upon maximum segment lifetime in the internet system of which the host is a part. In the paragraphs below, an explanation for this specification is given. TCP implementers may violate the quiet time restriction, but only at the risk of causing some old data to be accepted as new, or new data rejected as old duplicated by some receivers in the internet system. TCPs consume sequence number space each time a segment is formed and entered into the network output queue at a source host. The duplicate detection and sequencing algorithm in the TCP protocol relies on the unique binding of segment data to sequence space to the extent that sequence numbers will not cycle through all 2 to the 32 values before the segment data bound to those sequence numbers has been delivered and acknowledged by the receiver, and all duplicate copies of the segments have been drained from the internet. Without such an assumption, 2 distinct TCP segments could conceivably be assigned the same or overlapping sequence numbers, causing confusion at the receiver as to which data is new and which is old. Remember that each segment is bound to as many consecutive sequence numbers as there are octets of data in the segment. Under normal conditions, TCPs keep track of the next sequence number to emit and the oldest awaiting acknowledgement so as to avoid mistakenly using a sequence number over before its first use has been acknowledged. This alone does not guarantee that old duplicate data is drained from the net, so the sequence space has been made very large to reduce the probability that a wandering duplicate will cause trouble upon arrival. At 2 megabits per second, it takes 4.5 hours to use up 2 to the 32 octets of sequence space. Since the maximum segment lifetime in the net is not likely to exceed a few tens of seconds, this is deemed ample protection for foreseeable nets, even if the data rates escalate to tens of megabits per second. At 100 megabits per second, the cycle time is 5.4 minutes, which may be a little short, but still within reason. So this is a really good point about, like, this doesn't work, right? When you're using numbers within a sequence to be basically an identifier of what that sequence chunk is, it doesn't work if you're on a circular buffer, which is what it is. It's like mod 32, because if you're going fast enough, just think about it theoretically like this. I'm shooting data, and I shoot data really, really fast, but it still takes a couple chunks to do it. But it's really fast, faster than it could like drain in the internet or anything. So the middle chunk of my TCP segment that I send doesn't go through on the first route, but I actually get fully around the entire cycle all the way back to that, and I send another one that looks just like it, but is actually from new data and not old data. And this is like the problem that they're talking about. Okay, so let's continue. The basic duplicate detection and sequencing algorithm in TCP can be defeated. However, if a source TCP does not have any memory of the sequence numbers it last used on a given connection. For example, if the TCP were to start all connections with sequence number 0, then upon crashing and restarting, a TCP might reform an earlier connection, possibly after half-open connection resolution, and emit packets with sequence numbers identical to or overlapping with packets still in the network which were emitted on an earlier incarnation of the same connection. In the absence of knowledge about the sequence numbers used on a particular connection, the TCP specification recommends that the source delay for the MSL seconds before emitting segments on the connection to allow time for segments from earlier connection incarnation to drain from the system. Even hosts which can remember the time of day and use it to select initial sequence number values are not immune from this problem, i.e. even if the time of day is used to select an initial sequence number for each new connection incarnation. Alright, suppose for example that a connection is opened starting with the sequence number S. Suppose that this connection is not used much and that eventually the initial sequence number function, or ISN of t, takes on a value equal to the sequence number. Say S1 of the last segment sent by this TCP on a particular connection. Now suppose at this instance the host crashes, recovers, and establishes a new incarnation of the connection. The initial sequence number chosen is S1, which equals the ISN of t, the last used sequence number on old incarnation of the connection. If the recovery occurs quickly enough, any old duplicates in the net bearing sequence numbers in the neighborhood of S1 may arrive and be treated as new packets by the receiver of the new incarnation of the connection. The problem is that the recovering host may not know for how long it crashed, nor does it know whether there are still old duplicates in the system from earlier connection incarnations. One way to deal with this problem is to deliberately delay emitting segments for one MSL after recovery from a crash. This is the quiet times specification. Hosts which prefer to avoid waiting are willing to risk possible confusion of old and new packets at a given destination, may choose not to wait for the quiet time. Implementers may provide TCP users with the ability to select on a connection by connection basis whether to wait after a crash, or maybe informally implement the quiet time for all connections. Obviously, even where a user selects to wait, this is not necessary after the host has been up for at least MSL seconds. To summarize, every segment emitted occupies one or more sequence numbers in the sequence space. The numbers occupied by a segment are busy or in use until MSL seconds have passed. Upon crashing, a block of spacetime is occupied by the octets of the last emitted segment. If a new connection is started too soon and uses any of the sequence numbers in the spacetime footprint of the last segment of the previous connection incarnation, there is a potential sequence number overlap area which could cause confusion at the receiver. What a brilliant way. I mean, this was just maybe I was just ready for this at this exact moment, but this makes so much sense to me and is a really good way of explaining that entire thing. Section 3.4, Establishing a connection. The three-way handshake is the procedure used to establish a connection. This procedure normally is initiated by one TCP and responded to by another TCP. The procedure also works if two TCPs simultaneously initiate the procedure. When simultaneous attempts occur, each TCP receives a send segment which carries no acknowledgement after it has sent a send. Of course, the arrival of an old duplicate send segment can potentially make it appear to the recipient that a simultaneous connection initiation is in progress. Proper use of reset segments can disambiguate these cases. Several examples of connection initiation follow. Although these examples do not show connection synchronization using data carrying segments, this is perfectly legitimate so long as the receiving TCP doesn't deliver the data to the user until it is clear the data is valid, i.e. the data must be buffered at the receiver until the connection reaches the established state. The three-way handshake reduces the possibility of false connections. It is the implementation of a trade-off between memory and messages to provide information for this checking. The simplest three-way handshake is shown in Figure 7 below. The figure should be interpreted in the following way. Each line is numbered for reference purposes. Right arrows indicate departure of a TCP segment from TCP A to TCP B, or arrival of a segment at B from A. Left arrows indicate the reverse. Ellipsis indicates a segment which is still in the network, or delayed. An XXX indicates a segment which is lost or rejected. Comments appear in parentheses. TCP states represent the state after the departure or arrival of the segment, whose contents are shown in the center of each line. Segment contents are shown in abbreviated form with sequence number, control flags, and ACK field. Other fields such as window addresses, lengths, and text have been left out in the interest of clarity. And here you have TCP-A, and you have it's closed, and TCP-B is listening. TCP-A sends SYN with a sequence number of 100 and a control as SYN to TCP-B. And then TCP-B changes to being SYN receive state. From here, it basically responds back with the sequence number 300, the acknowledgement 101, and the control SYN ACK, which basically it's giving its sequence number, which is different, and then it's acknowledging its sequence number. And at this point in time, TCP-A is synchronized and said that the connection is established. Now that the connection is established, we're going to send basically sequence 101, and we're going to acknowledge 301. And we're going to send a control, which is ACK. And then at this point in time, we continue to send data, which is, with this data thing. Basic three-way handshake for connection synchronization. In line 2 of Figure 7, TCP-A begins by sending a SYN segment indicating that it will use sequence numbers starting with sequence number 100. In line 3, TCP-B sends a SYN and acknowledges the SYN it received from TCP-A. Note that the acknowledgement field indicates TCP-B is now expecting to hear sequence 101, acknowledging the SYN which occupied sequence 100. At line 4, TCP-A responds with an empty segment containing an ACK for TCP-B's SYN. And in line 5, TCP-A sends some data. Note that the sequence number of the segment in line 5 is the same as in line 4 because the ACK does not occupy sequence number space. If it did, we would wind up ACKing ACKs. I didn't really get this. My mind kind of was thinking about something else for a second, but simultaneous initiation is only slightly more complex and is shown in Figure 8. Each TCP cycles from closed to SYN sent to SYN received to established. They're both closed. And then this does a SYN sent, which is a sequence number 1 and control. And this does a SYN sent, which is a sequence number 300 with a control. Neither of them has gotten the ACK yet. This gets SYN received, and then it basically is going to, and this gets SYN received as well. Then from here it's going to respond with an ACK and send its same sequence number again. And from here, this thing is going to respond with an ACK and send its sequence number again. And at this point in time, both of them are connected and simultaneous connection synchronization. The principal reason for the three-way handshake is to prevent old duplicate connection initiations from causing confusion. To deal with this, a special control message reset has been devised. If the receiving TCP is in a non-synchronized state, i.e. SYN sent, SYN received, it returns to listen on receiving an acceptable reset. If the TCP is in one of the synchronized states, such as established, fin wait 1, fin wait 2, close wait, closing, last ACK, and time wait, it aborts the connection and informs its user. We discussed this later in the case of half-open connections below. It's so interesting how they've thought of every single possibility here and how basically these two things get into states and how to handle that. It's very interesting. Okay, we have another diagram, TCP-A, TCP-B. This one starts in closed. This one's in listen. This one sends the SYN in, the SYN sent. This one changes to the received, SYN received state, or actually it gets a old message, which is sequence 90, and control SYN, and that puts this in the receive state. And then it responds back with sequence 300 ACK91 control SYN ACK. But then this one sends SYN sent sec91 control reset, and now this goes back to the listen state, and now this one sends the new sequence number again, which is 100, and then this basically gets synced up this way. It acknowledges it and sends its own sequence number, and then the connection is established again. So basically you use the reset control bit to basically do that shift. As a simple example of recovery from old duplicates, consider figure 9 at line 3. An old duplicate SYN arrives at TCP-B. TCP-B cannot tell that this is an old duplicate, so it responds normally. TCP-A detects that the ACK field is incorrect and returns a reset with its sec field selected to make the segment believable. TCP-B, on receiving the RST, returns to the listen state when the original SYN, pun intended, finally arrives at line 6. Desynchronization proceeds normally. If the SYN at line 6 has arrived before RST, more complex exchange might have occurred with RSTs sent in both directions. The next section is titled Half-Open Connections and Other Anomalies. An established connection is said to be half-open if one of the TCPs has closed or aborted the connection at its end without the knowledge of the other, or if the two ends of the connection have become desynchronized owing to a crash that resulted in loss of memory. Such connections will automatically become reset if an attempt is made to send data in either direction. However, half-open connections are expected to be unusual, and the recovery procedure is mildly involved. If at Site A the connection no longer exists, then an attempt by the user at Site B to send any data on it will result in Site B TCP receiving a reset control message. Such a message indicates to the Site B TCP that something is wrong, and it is expected to abort the connection. Assume that two user processes A and B are communicating with one another when a crash occurs, causing loss of memory to A's TCP. Depending on the operating systems supporting A's TCP, it is likely that some error recovery mechanism exists. When the TCP is up again, A is likely to start again from the beginning or from a recovery point. As a result, A will probably try to open the connection again or try to send on the connection it believes open. In the latter case, it receives the error message "connection not open" from the local A's TCP. In an attempt to establish the connection, A's TCP will send a segment containing SYN. This scenario leads to the example shown in Figure 10. After TCP-A crashes, the user attempts to reopen the connection. TCP-B, in the meantime, thinks the connection is open. So here we have they were connected, and then TCP-A has a crash. TCP-B sends 300 and receives 100. TCP-A is in the closed state. TCP-B is in the established state. TCP-A sends SYN sent with the sequence number 400 and a control of SYN. TCP-B is confused, and then TCP-B sends back a message which is sequence number 300, acknowledge 100, control ACK. Control equals ACK, and 4 is confused, so then 4 is like SYN sent sequence number 100 control reset, and then TCP-B aborts the established connection it had before, and it goes into the closed state, and then finally SYN sent with the sequence number 400 and control SYN is sent, and it will correctly establish the connection. When SYN arrives at line 3, TCP-B, being in a synchronized state and the incoming segment outside the window, responds with an acknowledgement indicating what sequence it next expects to hear. ACK 100. TCP-A sees the segment, does not acknowledge anything sent it sent being unsynchronized, sends a reset because it has detected a half-open connection. TCP-B aborts at line 5. TCP-A will continue to try to establish the connection. The problem is now reduced to the basic three-way handshake. An interesting alternative case occurs when TCP-A crashes and TCP-B tries to send data on what it thinks is a synchronized connection. This is illustrated in figure 11. In this case, the data arriving at TCP-A from TCP-B is unacceptable because no connection exists, so TCP-A sends an RST. The RST is acceptable, so TCP-B processes it and aborts the connection. Then we have another example here where TCP-A sends or it crashes, and then TCP-B has still established a connection with something else, but TCP-A doesn't recognize what it does, so it just resets it. Basically, if one of the systems detects the other one is like out of sync, then it'll send this RST control bit. In figure 12, we find that two TCPs A and B with passive connections waiting for SYN. An old duplicate arriving at TCP-B stirs B into action. A SYN ACK is returned and causes TCP-A to generate an RST. TCP-B accepts the reset and returns to its passive listen state. Here we have a new example. TCP-A is in the listen state, TCP-B is in the listen state, and then TCP-A sends a sequence number Z and a SYN bit, and TCP-B becomes in the SYN receive state. Then TCP-B sends a sequence X and then an acknowledgement Z+1, and the control is SYN ACK. TCP-A is confused by this, so TCP-A sends a sequence number of Z+1 and a control of RST, and this makes TCP-B return to listen, and then they both go to the listen state. Old duplicate SYN initiates a I'm not really sure. Old duplicate SYN initiates a reset on two passive sockets. A variety of other cases are possible, all of which are accounted for by the following rules for RST generation and processing. RST reset generation. As a general rule, reset must be sent whenever a segment arrives, which apparently is not intended for the current connection. A reset must not be sent if it is not clear that this is the case. There are three groups of states. If the connection does not exist or is closed, then a reset is sent in response to any incoming segment except another reset. In particular, SYNs addressed to a non-existent connection are rejected by this means. If the incoming segment has an ACK field, the reset takes its sequence number from the ACK field of the segment. Otherwise, the reset has sequence number 0 and the ACK field is set to the sum of the sequence number and the segment length of the incoming segment. The connection remains in the closed state. 2. If the connection is in a non-synchronized state, listen, SYN sent, SYN received, and the incoming segment acknowledges something not yet sent, the segment carries an unacceptable ACK. Or if an incoming segment has a security level or compartment which does not exactly match the level and compartment requested, reset is sent. If our SYN has not been acknowledged and the precedence level of the incoming segment is higher than the precedence level requested, then either raise the local precedence level if allowed by the user and the system, or send a reset, or if the precedence level of the incoming segment is lower than the precedence level requested, then continue as if the precedence matched exactly. If the remote TCP cannot raise the precedence level to match ours, this will be detected in the next segment it sends, and the connection will be terminated then. If our SYN has been acknowledged, perhaps in this incoming segment, the precedence level of the incoming segment must match the local precedence level exactly. If it does not, a reset must be sent. If the incoming segment has an ACK field, the reset takes its sequence number from the ACK field of the segment. Otherwise, the reset has sequence number 0 and the ACK field is set to the sum of the sequence number and the segment length of the incoming segment. The connection remains in the same state. 3. If the connection is in the synchronized state, which is one of established, fin wait 1, fin wait 2, close wait, closing, last ACK, and time wait, any unacceptable segment out of the window sequence number or unacceptable acknowledgement number must elicit only an empty acknowledgement segment containing the current SYN sequence number and an acknowledgement indicating the next sequence number expected to be received, and the connection remains in the same state. If an incoming segment has a security level or compartment or precedence which does not exactly match the level in compartment and precedence requested for the connection, A reset is sent and the connection goes back to the closed state. The reset takes its sequence number from the ACK field of the incoming sequence, or the incoming segment. Reset processing. In all states except send, all reset segments are validated by checking their sequence number fields. A reset is valid if its sequence number is in the window. In the send state, a reset received in response to an initial send, the reset is acceptable if the ACK field acknowledges the send. The receiver of an RST first validates it, then changes state. If the receiver was in the listen state, it ignores it. If the receiver was in the send receive state and had previously been in the listen state, then the receiver returns to the listen state. Otherwise, the receiver aborts the connection and goes to the closed state. If the receiver was in any other state, it aborts the connection and advises the user and goes to the closed state. Section 3.5, closing a connection. Close is an operation meaning I have no more data to send. The notion of closing a full duplex connection is subject to ambiguous interpretation. Of course, since it may not be obvious how to treat the receiving side of the connection, we have chosen to create close in a simplex fashion. The user who closes may continue to receive until he is told that the other side is closed also. Thus, a program could initiate several sends followed by a close, and then continue to receive until signaled that a receive failed because the other side has closed. We assume that the TCP will signal the user even if no receives are outstanding, that the other side has closed so the user can terminate his side gracefully. A TCP will reliably deliver all buffers sent before the connection was closed, so a user who expects no data in return need only wait to hear the connection was closed successfully to know that all his data was received at the destination TCP. Users must keep reading connections they close for sending until the TCP says there is no more data. There are essentially three cases. The user initiates by telling the TCP to close the connection. 2, the remote TCP initiates by sending a fin control signal. And 3, both users close simultaneously. Case 1, local user initiates the close. In this case, a fin segment can be constructed and placed on the outgoing segment queue. No further sends from the user will be accepted by the TCP, and it enters the fin wait 1 state. Receives are allowed in this state. All segments preceding and including fin will be retransmitted until acknowledged. When the other TCP has both acknowledged the fin and sent a fin of its own, the first TCP can ACK this fin. Note that a TCP receiving a fin will ACK, but not send its own fin until its user has closed the connection also. Case 2, TCP receives a fin from the network. If an unsolicited fin arrives from the network, the receiving TCP can ACK it and tell the user that the connection is closing. The user will respond with a close, upon which the TCP can send a fin to the other TCP after sending any remaining data. The TCP then waits until its own fin is acknowledged, whereupon it deletes the connection. If an ACK is not forthcoming after the user timeout, the connection is aborted and the user is told. Case 3, both users close simultaneously. A simultaneous close by users at both ends of a connection causes fin segments to be exchanged. When all segments preceding the fins have been processed and acknowledged, each TCP can ACK the fin it has received. Both will, upon receiving these ACKs, delete the connection. Then we have another example here where TCP-A is established, TCP-B is established, then TCP-A sends fin wait 1 because it's closing its connection. This includes a sequence number and an acknowledgement number, but the control is fin ACK. TCP-B receives this and it enters the closed wait state. In the closed wait state, it sends its own message back to TCP-A. This has a sequence number and an acknowledgement number, and it has a control of ACK in it. Then TCP-A enters fin wait 2 because it's been acknowledged by the other side, and then here it's going to just wait itself until basically TCP-B sends its own fin ACK. And TCP-B closes its connection where the user closes it, and what it does is it sends a sequence number and an acknowledgement number, and it sends a control of fin ACK. At this point in time, TCP-A receives that, and it's still in the time wait state, and it sends back the sequence. It sends to TCP-B sequence 101, ACK 301, and then control ACK. And at this point in time, both sides have sent their fin information, which has also been acknowledged by both sides. And then they both are closed. The normal close sequence is what that's called. Then we have a simultaneous close sequence. TCPA is established, TCPB is established. Then TCPA sends a fin wait 1, and then TCPB sends a fin wait 1 at the same time. And remember, a fin wait 1 message has a sequence, an ACK, and then a control of fin ACK. Right? Then they both are entering the closing state. And when they're in the closing state, they both send an ACK for the fin ACK that they just saw. They both enter the time wait state, and then they close. Section 3.6, Precedence and Security. The intent is that connection be allowed only between ports operating with exactly the same security and compartment values, and at the higher of the precedence level requested by the two ports. The precedence and security parameters used in TCP are exactly those defined in the Internet Protocol. Throughout this TCP specification, the term security compartment is intended to indicate the security parameters used in IP, including security, compartment, user group, and handling restriction. A connection attempt with mismatched security compartment values or a lower precedence value must be rejected by sending a reset. Rejecting a connection due to too low a precedence only occurs after an acknowledgement of the send has been received. Note that TCP modules which operate only at the default value of precedence will still have to check the precedence of incoming segments and possibly raise the precedence level they use on the connection. The security parameters may be used in a non-secure environment. The values would indicate unclassified data. Thus, hosts in non-secure environments must be prepared to receive the security parameters, though they need not send them. Section 3.7, Data Communication. Once the connection is established, data is communicated by the exchange of segments. Because segments may be lost due to errors, checksum test failure, or network congestion, TCP uses retransmission after a timeout to ensure delivery of every segment. Duplicate segments may arrive due to network or TCP retransmission. As discussed in the section on sequence numbers, the TCP performs certain tests on the sequence and acknowledgement numbers in the segments to verify their acceptability. The sender of data keeps track of the next sequence number to use in the variable send.next. The receiver of data keeps track of the next sequence number to expect in the variable receive.next. The sender of data keeps track of the oldest unacknowledged sequence number in the variable send.unacknowledged. If the data flow is momentarily idle and all data sent has been acknowledged, then the three variables will be equal. When the sender creates a segment and transmits it, the sender advances send.next. When the receiver accepts a segment, it advances receive.next and sends an acknowledgement. When the data sender receives an acknowledgement, it advances send.unacknowledged. The extent to which the values of these variables differ is a measure of the delay in the communication. The amount by which the variables are advanced is the length of the data in the segment. Note that once in the established state, all segments must carry current acknowledgement information. The close user call implies a push function, as does the fin control flag in an incoming segment. Retransmission timeout. Because of the variability of networks that compose an inter-network system and the wide range of uses of TCP connections, the retransmission timeout must be dynamically determined. One procedure for determining a retransmission timeout is given here as an illustration. An example of retransmission timeout procedure. Measure the elapsed time between sending a data octet with a particular sequence number and receiving an acknowledgement that covers that sequence number. Segments sent do not have to match the segments received. This measured elapsed time is the round trip time. Next, compute a smooth round trip time, or SRTT, as SRTT equals alpha times SRTT plus 1 minus alpha times RTT. And based on this, compute the retransmission timeout, or RTO, which is RTO is the minimum between the upper bound and the max of the lower bound, and the beta times SRTT, where upper bound is the upper bound on the timeout, e.g. 1 minute, lower bound is the lower bound on the timeout, e.g. 1 second, alpha is a smoothing factor, e.g. 0.8 to 0.9, and beta is a delay variance factor, e.g. 1.3 to 2.0. The communication of urgent information. The objective of the TCP urgent mechanism is to allow the sending user stimulate the receiving user to accept some urgent data and to permit the receiving TCP to indicate to the receiving user when all the currently known urgent data has been received by the user. This mechanism permits a point in the data stream to be designated as the end of urgent information whenever this point is in advance of the received sequence number or the receive.next variable at the receiving TCP. That TCP must tell the user to go into urgent mode when the received sequence number caches up to the urgent pointer. The TCP must tell the user to go into the normal mode. If the urgent pointer is updated while the user is in urgent mode, the update will be invisible to the user. This method employs an urgent field which is carried in all segments transmitted. The urge control flag indicates that the urgent field is meaningful and must be added to the segment sequence number to yield the urgent pointer. The absence of this field indicates that there is no urgent data outstanding. To send an urgent indication, the user must also send at least one data octet. If the sending user also indicates a push, timely delivery of the urgent information to the destination process is enhanced. Managing the window. The window sent in each segment indicates the range of a sequence numbers the sender of the window, the data receiver, is currently prepared to accept. There is an assumption that this is related to the currently available data buffer space available for this connection. Indicating a large window encourages transmissions. If more data arrives than can be accepted, it will be discarded. This will result in excessive retransmissions, adding unnecessarily to the load of the network and the TCPs. Indicating a small window may restrict the transmission of data to the point of introducing a round-trip delay between each new segment transmitted. The mechanisms provided allow a TCP to advertise a large window and to subsequently advertise a much smaller window without having accepted that much data. This so-called shrinking the window is strongly discouraged. The Robustness Principle dictates that TCPs will not shrink the window themselves, but will be prepared for such behavior on the part of other TCPs. Okay. The sending TCP must be prepared to accept from the user and send at least one octet of new data even if the send window is 0. The sending TCP must regularly retransmit to the receiving TCP even when the window is 0. 2 minutes is recommended for the retransmission interval when the window is 0. This retransmission is essential to guarantee that when either TCP has a 0 window, the reopening of the window will be reliably reported to the other. When the receiving TCP has a 0 window and a segment arrives, it must still send an acknowledgment sharing its next expected sequence number and current window. The sending TCP packages the data to be transmitted into segments which fit the current window and may repackage segments on the retransmission queue. Such repackaging is not required but may be helpful. If a connection with a one-way data flow, in a connection with a one-way data flow, the window information will be carried in acknowledgement segments that all have the same sequence number, so there will be no way to reorder them if they arrive out of order. This is not a serious problem, but it will allow the window information to be on occasion temporarily based on old reports from the data receiver. A refinement to avoid this problem is to act on the window information from segments that carry the highest acknowledgement number, that is, segments with the acknowledgement number equal to or greater than the highest previously received. The window management procedure has significant influence on the communication performance. The following comments are suggestions to implementers. Window management suggestions. Allocating a very small window causes data to be transmitted in many small segments Allocating a very small window causes data to be transmitted in many small segments when better performance is achieved using fewer, larger segments. One suggestion for avoiding small windows is for the receiver to defer updating a window until the additional allocations is at least X% of the maximum allocation possible for the connection, where X might be 20 to 40. Another suggestion is for the sender to avoid sending small segments by waiting until the window is large enough before sending data. If the user signals a push function, then the data must be sent even if it is a small segment. Note that the acknowledgments should not be delayed or unnecessary retransmissions will result. One strategy would be to send an acknowledgment when a small segment arrives without updating the window information, and then to send another acknowledgment with the new window information when the window is larger. The segment sent to probe a 0 window may also begin a breakup of transmitted data into smaller and smaller segments. If a segment containing a single data octet sent to probe a 0 window is accepted, it consumes 1 octet of the window now available. If the sending TCP simply sends as much as it can whenever the window is non-zero, the transmitted data will be broken into alternating big and small segments. As time goes on, occasional pauses in the receiver making window allocation available will result in breaking the big segments into a small and not quite so big pair. And after a while, the data transmission will be mostly small segments. The suggestion here is that the TCP implementations need to actively attempt to combine small window allocations into larger windows, since the mechanisms for managing the window tend to lead to many small windows and the simplest minded implementations. So I'm going to take a break now because it's just really hard to read this for so long. So I'll pick up at section 3.8 interfaces pretty soon. Alright guys, it's a new day, but I'm going to pick up from where I left off in the last chunk. And this is section 3.8 interfaces of RFC 79 or 793 on the TCP protocol. There are, of course, 2 interfaces of concern, the user TCP interface and the TCP/lower level interface. We have a fairly elaborate model of the user TCP interface, but the interface to the lower level protocol module is left unspecified here, since it will be specified in detail by the specification of the lower level protocol. For the case that the lower level is IP, we note some of the parameter values that TCPs might use. User/TCP interface. The following functional description of user commands to the TCP is, at best, fictional, since every operating system will have different facilities. Consequently, we must warn readers that different TCP implementations may have different user interfaces. However, all TCPs must provide a certain minimum set of services to guarantee that all TCP implementations can support the same protocol hierarchy. This section specifies the functional interfaces required of all TCP implementations. The TCP user commands. The following sections functionally characterize a user TCP interface. The notation used is similar to most procedure or function calls in high-level languages, but this usage is not meant to rule out trap-type service calls, e.g. SVCs, UUOs, and EMTs. The user commands described below specify the basic functions the TCP must perform to support inter-process communication. Individual implementations must define their own exact format and may provide combinations or subsets of the basic functions in single calls. In particular, some implementations may wish to automatically open a connection on the first send or receive issued by the user for a given connection. In providing inter-process communication facilities, the TCP must not only accept commands, but also return information to the process it serves. The latter consists of A. General information about connection, e.g. interrupts, remote close, binding of unspecified foreign socket, and B. Replies of specific user commands indicating success or various types of failure. Open. Format is open, local port, foreign socket, active passive, timeout optionally, precedence optionally, security compartment optionally, options optionally. And then it returns a local connection and name. We assume that the local TCP is aware of the identity of the process it serves and will check the authority of the process to use the connection specified. Depending upon the implementation of the TCP, the local network and TCP identifiers for the source address will either be supplied by the TCP or the lower level protocol, e.g. IP. These considerations are the result of concern about security to the extent that no TCP be able to masquerade as another, and so on. Similarly, no process can masquerade as another without the collusion of the TCP. If the active passive flag is set to passive, and this is a call to listen, if the active passive flag is set to passive, then this is a call to listen for an incoming connection. A passive open may have either a fully specified foreign socket to wait for a particular connection or an unspecified foreign socket to wait for any call. A fully specified passive call can be made active by the subsequent execution of a send. a transmission control block, or TCB, is created and partially filled in with data from the open command parameters. On an active open command, the TCP will begin the procedure to synchronize, i.e. establish the connection at once. The timeout, if present, permits the caller to set up a timeout for all data submitted to TCP. If data is not successfully delivered to the destination within the timeout period, the TCP will abort the connection. The present global default is 5 minutes. 2. The TCP or some component of the operating system will verify the user's authority to open a connection with the specified precedence or security compartment. 1. The absence of precedence or security compartment specification in the open call indicates the default values must be used. 2. TCP will accept incoming requests as matching only if the security compartment information is exactly the same and only if the precedence is equal to or higher than the precedence requested in the open call. 1. The precedence for the connection is the higher of the values requested in the open call and received from the incoming request, and fixed at that value for the life of the connection. Implementers may want to give the user control of this precedence negotiation. For example, the user might be allowed to specify that the precedence must be exactly matched, or that any attempt to raise the precedence be confirmed by the user. A local connection name will be returned to the user by the TCP. The local connection name can then be used as a shorthand term for the connection defined by the local socket foreign socket pair. Send. The format is it's a function called send, and it accepts a local connection name, a buffer address, a byte count, a push flag, and an urgent flag, and an optional timeout argument. This call causes the data contained in the indicated user buffer to be sent on the indicated connection. If the connection has not been opened, the send is considered an error. Some implementations may allow users to send first, in which case an automatic open would be done. If the calling process is not authorized to use this connection, an error is returned. 2. If the push flag is set, the data must be transmitted promptly to the receiver, and the push bit will be set in the last TCP segment created from the buffer. 1. If the push flag is not set, the data may be combined with data from subsequent sends for transmission efficiency. 2. If the urgent flag is set, segments sent to the destination TCP will have the urgent pointer set. The receiving TCP will signal the urgent condition to the receiving process if the urgent pointer indicates that data preceding the urgent pointer has not been consumed by the receiving process. The purpose of urgent is to stimulate the receiver to process the urgent data and to indicate to the receiver when all the currently known urgent data has been received. The number of times the sending user's TCP signals urgent will not necessarily be equal to the number of times the receiving user will be notified of the presence of urgent data. If no foreign socket was specified in the open, but the connection is established, e.g. because a listening connection has become specific due to a foreign segment arriving for the local socket, then the designated buffer is sent to the implied foreign socket. Users who make use of open with an unspecified foreign socket can make use of send without ever explicitly knowing the foreign socket address. 0. However, if a send is attempted before the foreign socket becomes specified, an error will be returned. 2. Users can use the status call to determine the status of the connection. 2. In some implementations, the TCP may notify the user when an unspecified socket is bound. 1. If a timeout is specified, the current user timeout for this connection is changed to the new one. 2. In the simplest implementation, send would not return control to the sending process until either the transmission was complete or the timeout had been exceeded. 1. However, this simple method is both subject to deadlocks. For example, both sides of the connection might try to do sends before doing any receives, and offers poor performance, so it is not recommended. 1. A more sophisticated implementation would return immediately to allow the process to run concurrently with network I/O, and furthermore, to allow multiple sends to be in progress. 1. Multiple sends are served in first-come, first-served order, so the TCP will queue those it cannot service immediately. 2. We have implicitly assumed an asynchronous user interface in which a send later elicits some kind of signal or pseudo-interrupt from the serving TCP. 1. An alternative is to return a response immediately. For instance, sends might return immediate local acknowledgement even if the segment sent had not been acknowledged by the distant TCP. We could optimistically assume eventual success. If we are wrong, the connection will close anyway due to the timeout. In implementations of this kind, synchronous, there will still be some asynchronous signals, but these will deal with the connection itself and not with specific segments or buffers. In order for the process to distinguish among error or success indications for different sends, it might be appropriate for the buffer address to be returned along with the coded response to the send request. TCP-2 user signals are discussed below, indicating the information which should be returned to the calling process. This is kind of interesting because simultaneously while going through this TCP stuff, I've also been looking deeper into Python's async IO implementation. And it's interesting to see in this document in 1981, like 40 years ago, because it's 2021 right now, they were basically already juggling asynchronous versus synchronous type of stuff. And really, Python didn't get it until almost 35 years. I think async IO's first PEP was in 2015 or something. Maybe it was a little bit earlier. But basically, it just shows how, although we think about technology as kind of growing in this sort of singularity, exponential, just extremely fast, it takes people right now to move technology forward. And people are not exponential beyond the population growing exponentially until it stops, which it has. And also, the people that are actually going to do this work are a very small fraction of the global population. And so it's although I think that just increasing the number of people should also increase the number of these type of special people that create these technological innovations. So it's just interesting to actually kind of have a little bit of real data about some of these things when they were first discussed, and they probably wasn't first discussed here either. Who knows? Maybe the first mention of this was 20 years before even this document. I don't know. But this is just kind of an aside that stands out to me. So I'm going to continue. The receive function. Receive, it passes a local connection name, a buffer address, a byte count, and it returns a byte count, an urgent flag, and a push flag. Okay, this command allocates a receiving buffer associated with the specified connection. If no open precedes this command, or the calling process is not authorized to use this connection, an error is returned. In the simplest implementation, control would not return to the calling program until either the buffer was filled or some error occurred, but this scheme is highly subject to deadlocks. A more sophisticated implementation would permit several receives to be outstanding at once. These would be filled as segments arrive. This strategy permits increased throughput at the cost of a more elaborate scheme, possibly asynchronous, to notify the calling program that a push has been seen or a buffer filled. If enough data arrives to fill the buffer before a push is seen, the push flag will not be set in the response to the receive. The buffer will be filled with as much data as it can hold. If a push is seen before the buffer is filled, the buffer will be returned partially filled and push indicated. If there is urgent data, the user will have been informed as soon as it arrived via a TCP to user signal. The receiving user should thus be in urgent mode. If the urgent flag is on, additional urgent data remains. If the urgent flag is off, this call to receive has returned all the urgent data, and the user may now leave urgent mode. Note that data following the urgent pointer, non-urgent data, cannot be delivered to the user in the same buffer with preceding urgent data unless the boundary is clearly marked for the user. To distinguish among several outstanding receives and to take care of the case that a buffer is not completely filled, the return code is accompanied by both a buffer pointer and a byte count indicating the actual length of the data received. Alternative implementations of receive might have the TCP allocate buffer storage, or the TCP might share a ring buffer with the user. Close. Format. Close local connection name. This command causes the connection specified to be closed. If the connection is not open or the calling process is not authorized to use this connection, an error is returned. Closing connections is intended to be a graceful operation in the sense that outstanding sends will be transmitted and retransmitted as flow control permits until all have been serviced. Thus, it should be acceptable to make several send calls followed by a close and expect all the data to be sent to the destination. It should also be clear that users should continue to receive on closing connections since the other side may be trying to transmit the last of its data. Thus, close means I have no more to send, but does not mean I will not receive any more. It may happen, if the user level protocol is not well thought out, that the closing side is unable to get rid of all its data before timing out. In this event, close turns into abort and the closing TCP gives up. The user may close the connection at any time on his own initiative or in response to various prompts from the TCP, e.g. remote close executed, transmission timeout exceeded, destination inaccessible. Because closing a connection requires communication with the foreign TCP, connections may remain in the closing state for a short time. Attempts to reopen the connection before the TCP replies to the close command will result in error responses. Close also implies push function. Status format. Status takes a local connection name and returns status data. This is an implementation dependent user command and could be excluded without adverse effect. Information returned would typically come from the TCB associated with the connection. This command returns a data block containing the following information: the local socket, the foreign socket, the local connection name, the receive window, the send window, the connection state, the number of buffers awaiting acknowledgement, the number of buffers pending receipt, urgent state, precedence, security and compartment, and the transmission timeout. Depending on the state of the connection or on the implementation itself, some of the information may not be available or meaningful. If the calling process is not authorized to use this connection, an error is returned. This prevents unauthorized processes from gaining information about a connection. Abort. Format abort. It takes a local connection name. This command causes all pending sends and receives to be aborted. The TCB, I forget what that's called now. Transmission control buffer? Block. Maybe? I think so. I know it's called the block. The TCB to be removed, and a special reset message to be sent to the TCP on the other side of the connection. Depending on the implementation, users may receive abort indications for each outstanding send or receive, or may simply receive an abort acknowledgement. TCP to user messages. It is assumed that the operating system environment provides a means for the TCP to asynchronously signal the user program. When the TCP does signal a user program, certain information is passed to the user. Often in the specification, the information will be an error message. In other cases, there will be information relating to the completion of processing a send or receive or other user call. The following information is provided: the local connection name. Basically, the local connection name is always provided. The response string is always provided. The buffer address, send and receive. I'm not sure. Oh, okay. Oh, I see. So if you're sending and receiving, if you're calling the send and receive message, or method, or like function, then it'll basically provide the buffer address. If you're sending the receive, it'll provide the byte count. If you're using the receive function, it provides the byte count, the push flag, the urgent flag. And then we have TCP lower level interface. The TCP calls on a lower level protocol module to actually send and receive information over a network. One case is that of the ARPA internetwork system, where the lower level module is the internet protocol. If the lower level protocol is IP, it provides arguments for a type of service and for a time to live. TCP uses the following settings for these parameters. Type of service equals precedence, routine, delay equals normal, and throughput equals normal, and reliability equals normal, or the value is 0000. It looks like it's a bit mask, basically. Time to live is 1 minute, or 00111100. Note that the assumed maximum segment lifetime is 2 minutes. Here we explicitly ask that a segment be destroyed if it cannot be delivered by the internet system within 1 minute. If the lower level is IP or other protocol that provides this feature, and source routing is used, the interface must allow the route information to be communicated. This is especially important so that the source and destination addresses used in the TCP checksum be the originating source and ultimate destination. It is also important to preserve the return route to answer connection requests. Any lower level protocol will have to provide the source address, destination address, and protocol fields, and some way to determine the TCP length, both to provide the functional equivalent service of IP and to be used in the TCP checksum. Section 3.9, Event Processing. The processing depicted in this section is an example of one possible implementation. Other implementations may have slightly different processing sequences, but they should differ from those in this section only in detail, not in substance. The activity of the TCP can be characterized as responding to events. The events that occur can be cast into three categories: user calls, arriving segments, and timeouts. This section describes the processing the TCP does in response to each of these events. In many cases, the processing required depends on the state of the connection. Events that occur: user calls, open, send, receive, close, abort, and status. So the user can call an open, and these are events basically. So one event is the user opening, user calling open. One event is the user calling send. Another is the user calling receive. Another is the user calling close. Another is the user calling abort. And another is the user calling status. Arriving segments is basically a separate section of events, and there's only one here, when a segment arrives. And basically the timeouts is the user timeout, the retransmission timeout, and the time wait timeout. These are all events that can happen. I'm not sure what the user timeout is. Maybe it's the user setting it. The retransmission timeout makes sense that like as the retransmission, there's like a retransmission buffer, right? And inside of that buffer is a timeout, like a timer for each one of those. And when those timers go off, that should trigger an event, which is going to retransmit. The time wait timeout is for the final state of when the socket has completely closed. And that similarly has an event that's going to be triggered when it's actually like completely shut down. The model of the TCP user interface is that user commands receive an immediate return and possibly a delayed response via an event or pseudo interrupt. In the following descriptions, the term signal means a delayed response. Error responses are given as character strings. For example, user commands referencing connections that do not exist receive error, connection not open. Please note in the following that all arithmetic on sequence numbers, acknowledgement numbers, windows, etc. is modulo 2 to the 32, the size of the sequence number space. Also note that equals to or less means less than or equal, 2 modulo 2 to the 32. A natural way to think about processing incoming segments is to imagine that they are first tested for proper sequence number, i.e. that their contents lie in the range of the expected receive window in the sequence number space, and then that they are generally queued and processed in sequence number order. When a segment overlaps other already received segments, we reconstruct the segment to contain just the new data and adjust the header fields to be consistent. Note that if no state change is mentioned, the TCP stays in the same state. Then we have the open call and the closed state, i.e. the TCP does not exist. So basically, if the TCP connection you have being managed by the operating system is in the closed state and the user calls open, what's going to happen is the operating system level is going to create a new transmission control block to hold connection state information. It's going to fill in the local socket identifier, the foreign socket, the precedence, the security compartment, and user timeout information. Note that some parts of the foreign socket may be unspecified in a passive open and are to be filled in by the parameters of the incoming SYN segment. Verify the security and precedence requested are allowed for this user. If not, return error, precedence not allowed, or error, security compartment not allowed. If passive enter the listen state and return. Okay, it enters the listen state and it returns. If active and the foreign socket is unspecified, return error, foreign socket unspecified. If active and the foreign socket is specified, issue a SYN segment. An initial SYN sequence number, ISS, is selected. A SYN segment of the form sequence ISS control equals SYN is sent. And then set the SYN dot unacknowledged to the ISS and the SYN dot next to the ISS plus 1. And then you enter the SYN sent state and return. It's pretty cool. It's telling you at very high fidelity what the basically TCP program is going to do. If the caller does not have access to the local socket specified, return error connection illegal for this process. If there is no room to create a new connection, return error insufficient resources. Listen state. If active and foreign socket is specified, then change the connection from passive to active and select an initial sequence number, right? Send a SYN segment, set the send unacknowledged number to the ISS, the send next number to the ISS plus 1, and enter the SYN sent state. The data associated with send may be sent with the SYN segment or queued for transmission after entering the established state. The urgent bit, if requested in the command, must be sent with the data segment sent as a result of this command. If there is no room to queue the request, respond with error insufficient resources. If foreign socket was not specified, then return error foreign socket unspecified. And then we have open call, and we have SYN sent state, SYN received state, established state, fin wait 1 state, fin wait 2 state, closing wait state, closing state, last act state, and time wait state. So what it's saying is in all of those states, basically, if you call open and you're not closed, then it returns an error connection already exists. Okay. Then you have the send call, which if you call send and the TCP program is in the closed state, or sorry, the TCP connection is in the closed state, i.e. the TCP does not exist, then it's going to say if the user does not have access to such a connection, then return error connection illegal for this process. Otherwise, return error connection does not exist. While if it's in the listen state, send is going to, if the foreign socket is specified, then change the connection from passive to active, select an ISS, send to send segment, set the send unacknowledged to the ISS, set the send next, next to ISS plus 1, and then enter the SYN sent state, and data associated with send may be sent with the send segment or queued for transmission after entering the established state. The urgent bit, if requested in the command, must be sent when the data segments send in the command must be sent with the data segments sent as a result of this command. If there is no room to queue the request, respond with the error insufficient resources. If foreign socket was not specified, then return the error foreign socket unspecified. If you send and you're in the SYN sent state or the SYN receive state, queue the data for transmission after entering the established state. If no space to queue, respond with the error insufficient resources. If you're in the established state or the closed wait state, then segmentize the buffer and send it with a piggybacked acknowledgement, where acknowledgement value equals receive.next. If there is insufficient space to remember this buffer, simply return error insufficient resources. If the urgent flag is set, then syn.up, then you store basically the syn.next -1 in the syn.up and set the urgent pointer in the outgoing segments. And then basically if you call syn when the TCP connection is in the fin wait 1 state, the fin 2 wait state, the closing state, the last act state, or the time wait state, you return the error connection closing and do not service the request. Okay, then we have the receive call. When the receive call is called and the connection is in the closed state, if the user does not have access to such a connection, return error connection illegal for this process. Otherwise, return error connection does not exist. If you try to receive and you're in the listen state, the SYN send state, or the SYN receive state, then queue for processing after entering the established state. If there is no room to queue this request, respond with error insufficient resources. If you try and receive and you're in the established state, the fin wait 1 state or the fin wait 2 state, if insufficient incoming segments are queued to satisfy the request, queue the request. If there is no queue space to remember the receive, respond with error insufficient resources, and then reassemble the queued incoming segments into a receive buffer and return it to the user. Mark push seen if this is the case. If receive.up is in the data, or if receive.up is in advance of the data currently being passed to the user, notify the user of the presence of urgent data. When the TCP takes responsibility for delivering data to the user, that fact must be communicated to the sender via an acknowledgment. The formation of such an acknowledgment is described below in the discussion of processing an incoming segment. When you call receive and you're in the close wait state, or the connection is in the close wait state, since the remote side has already sent fin, receives must be satisfied by text already on hand but not yet delivered to the user. If no text is awaiting delivery, the receive will get an error connection closing response. Otherwise, any remaining text can be used to satisfy the receive. If the receive call is called and you're in the closing state, the last ACK state, or the time wait state, return error connection closing. Then we have if you're in the close, if you call close and you're in the closed state, i.e. the TCP does not exist, if the user does not have access to such a connection, return error connection illegal for this process. Otherwise, return error connection does not exist. If you call close and you're in the listen state, any outstanding receives are returned with error closing responses. Delete the TCP and then enter the closed state and return. If you call close and you're in the SYN sent state, delete the TCP and return error closing responses to any queued SYNs or receives. If you're in the SYN received state, if no SYNs have been issued and there is no pending data to send, then form a fin segment and send it and enter the fin wait 1 state. Otherwise, queue for processing after entering the established state. If you're in the established state, queue this until all preceding SYNs have been segmentized, then form a fin segment and send it. In any case, enter fin wait 1 state. If you're in the fin wait 1 state and the fin wait 2 state, strictly speaking, this is an error and should receive an error connection closing response. An OK response would be acceptable too, as long as the second fin is not admitted. The first fin may be retransmitted though. And if you call close while you're in the closed wait state, queue this request until all preceding SYNs have been segmentized, then send a fin segment and enter the closing state. And if you're in the closing state, last ACK state, or time wait state, respond with error connection closing. I'm going to take a break here and come back in at this abort basically explanation. Alright guys, I'm back. Took a little bit of a break, but same day, and we're going to continue with what we were reading before. So this is the abort function. So if you call the abort function when your connection is in the closed state, if the user should not have access to such a connection, then return an error, connection illegal for this process. Otherwise, return error, connection does not exist. And then we have, if you call abort when you're in the listen state, any outstanding receives should be returned with error, connection reset, responses. And then you're going to delete the TCP, and then you're going to enter the closed state and return. And if you are in the SYN sent state, all queued SYNs and receives should be given connection reset notification, delete the TCP, and enter the closed state and return. And if you're in the SYN received, established, fin wait 1, fin wait 2, or closed wait state, then you're going to send a reset segment, which will look like the form sequence number equals syn.next and control equals RST. All queued SYNs and receives should be given connection reset should be given the connection reset notification, and all segments queued for transmission except for the RST formed above or retransmission should be flushed. Delete the TCP, enter the closed state, and return. If you call abort and you're in the closing state, last ACK state, or time wait state, respond with OK and delete the TCP, enter the closed state, and return. So if you call the status call and you're in the closed state, it'll do the same thing it has said before. It'll give you an error if it's legal for the process, or it'll give you an error because the connection does not exist. If you call status and you're in the listen state, it'll return state equals listen and the TCP pointer. If Here in the syn state, it'll return state equals syn and the TCP pointer. Basically, whatever state you're in, it'll return that state, and then it'll return the TCP pointer so that you can expect the details of the TCP protocol's state. And, alright, then we have the segment arrives event. Segment arrives event. If the state is closed, then all data in the incoming segment is discarded. An incoming segment containing an RST is discarded. An incoming statement not containing a RST causes a RST to be sent in response. The acknowledgment and sequence field values are selected to make the reset sequence acceptable to the TCP that sent the offending segment. If the ACK bit is off, the sequence number 0 is used. Sequence number equals 0, so basically it's going to send something that looks like sequence equals 0, ACK equals segment.sequence plus segment.length, and control equals RST ACK. If the ACK bit is on, it's going to look like sequence equals segment.ACK and control equals RST, and then it's going to return. If the state is listen, then it's going to first check for an RST, and an incoming RST should be ignored, and then it's going to return. It's going to second check for an ACK, and any acknowledgement is bad if it arrives on a connection still in the listen state. An acceptable reset segment should be formed for any arriving ACK-bearing segment. The RST should be formatted as follows, and it's going to be sequence equals segment.ACK and control equals RST. Then it's going to return. Third, it's going to check for a SYN. If the SYN bit is set, it's going to check the security. If the security compartment on the incoming segment does not exactly match the security compartment in the TCB, then send a reset and return. If the segment.prc is greater than the TCB.prc, which I think is the precedence, then if allowed by the user in the system, set the TCB's precedence to the segment's precedence. If not allowed, send a reset and return, which will look like sequence number equals segment.ACK and control equals RST. If the segment.prc is less than the TCB.prc, then continue. Set the receive.next to the segments.sequence plus 1, sequence number plus 1, and then the IRS is set to the segment.sequence number, and any other controller text should be queued for processing later. The ISS should be selected, and a SYN segment sent of the form of sequence number equals the ISS, ACK equals the receive.next, and control equals the SYN ACK. The SYN.next is set to the ISS plus 1, and the SYN.unacknowledged to ISS. The connection state should be changed to SYN received. Note that any other incoming control data, control or data combined with SYN will be processed in the SYN received state. But processing of SYN and ACK should not be repeated. If the listen was not fully specified, i.e. the foreign socket was not fully specified, then the unspecified field should be filled in now. Fourth, other text or control. Any other control or text-bearing segment not containing SYN must have an ACK and thus would be discarded by the ACK processing. An incoming RST segment could not be valid since it could not have been sent in response to anything sent by this incarnation of the connection, so you are unlikely to get here, but if you do, drop the segment and return. If the state is SYN sent, then first check the ACK bit. If the ACK bit is set, if the segment.ACK is less than or equal to the ISS, or the segment.ACK is greater than the SYN.next, send a reset unless the RST bit is set. If so, drop the segment and return. Sequence number equals segment.ACK and control equals RST, and discard the segment, return. If the SYN.unacknowledged is less than or equal to the segment.acknowledged, and that's less than or equal to the SYN.next, then the ACK is acceptable. Second, check the RST bit. So the next thing we have inside of this segment arrives event section is if the RST bit is set, if the acknowledgement was acceptable, then signal to the user error connection reset, drop the segment, enter the closed state, delete the TCB, and return. Otherwise, no ACK, drop the segment and return. Third, check the security and precedence. If the security compartment in the segment does not exactly match the security compartment in the TCB, send a reset. If there is an ACK, send the sequence number equals segment.ACK and control equals RST. Otherwise, sequence number equals 0 and ACK equals segment.sequence number plus segment.length and control RST ACK. If there is an ACK, the precedence in the segment must match the precedence in the TCB. If not, send a reset. And that will look like sequence number equals segment.ACK and control equals RST. If there is no ACK, if the precedence in the segment is higher than the precedence in the TCB, then if allowed by the user in the system, raise the precedence in the TCB to that in the segment. If not allowed to raise the precedence, then send a reset. And this will look like a sequence equals 0, an ACK equals segment.sequence number plus segment.length, and control equals RST ACK. If the precedence in the segment is lower than the precedence in the TCB, continue. If a reset was sent, discard that segment and return. Fourth, check the SYN bit. This step should be reached only if the ACK is okay, or there is no ACK, and if the segment did not contain an RST. If the SYN bit is on and the security compartment and precedence are acceptable, then receive.next is set to segment.sequence plus 1. IRS is set to segment.sequence number, and then the SYN.unacknowledged should be advanced to the equal segment.ACK if there is an ACK, and any segments on the retransmission queue which are thereby acknowledged should be removed. If SYN.unacknowledged is greater than the ISS or SYN has been ACKed, change the connection state to established, form an ACK statement that looks like sequence number equals SYN.next, acknowledgement number equals receive.next, and the control code equals ACK. Then you send it. Data or controls which were queued for transmission may be included. If there are other controls or text in the segment, then continue processing at the 6th step below where the urge bit is checked. Otherwise, return. Otherwise, enter SYN received, form a SYN ACK segment, which will look like sequence number equals the ISS, acknowledgement number equals the receive.next, and control equals the code for SYN ACK. Then you send that, and if there are other controls or text in the segment, queue them for processing after the established state has been reached, and then return. Fifth, if neither of the SYN or RST bits is set, then drop the segment and return. Otherwise, first check the sequence number, and if you're in the SYN receive state, the established state, the fin wait 1 state, the fin wait 2 state, the close wait state, the closing state, the last ACK state, or the time wait state, segments are processed in sequence. Initial tests on arrival are used to discard old duplicates, but further processing is done in the segment.sequence number order. If a segment's contents straddle the boundary between old and new, only the new parts should be processed. There are 4 cases for the acceptability test for an incoming segment. The first test is the segment.sequence number equals the receive.next number. The next test is the receive.next number is less than or equal to the segment's sequence number, or so the receive.next number is less than or equal to the segments.sequence number, which is less than the receive.next number plus the receive.window number. The next one is not acceptable, and the last one is the receive.next number is less than or equal to the segment.sequence number, which is less than the receive.next number plus the receive window number, or the receive.next number is less than or equal to the segment.sequence number plus the segment's length minus 1, and then that's less than the receive.next number plus the receive.window number. If the receive.window is 0, no segments will be acceptable, but special allowance should be made to accept valid ACKs, urge, and RSTs. If an incoming segment is not acceptable, an acknowledgement should be sent in reply unless the RST bit is set. If so, drop the segment and return. This will send a message that looks like sequence number equals SYN.next, acknowledgement equals receive.next, and control code equals ACK. After sending the acknowledgement, drop the unacceptable segment and return. In the following, it is assumed that the segment is the idealized segment that begins at receive.next and does not exceed the window. One could tailor actual segments to fit this assumption by trimming off any portions that lie outside the window, including SYN and fin, and only processing further if the segment then begins at receive.next. Segments with higher beginning sequence numbers may be held for later processing. And then Second, you check the RST bit, and if you're in the SYN receive state, if the RST bit is set, if this connection was initiated with a passive open, i.e. came from the listen state, then return this connection to the listen state and return. The user need not be informed. If this connection was initiated with an active open state, i.e. came from SYN sent state, then the connection was refused. Signal the signal to the user the connection was refused. In either case, all segments on the retransmission queue should be removed, and in the active open case, enter the closed state and delete the TCP and return. If you are in the established state, the fin wait 1 state, the fin wait 2 state, or the close wait state, if the RST bit is set, any outstanding receives and send should receive reset responses. All segment queues should be flushed. Users should also receive an unsolicited general connection reset signal, and then you should enter the closed state, delete the TCP, and return. If you are in the closing state, the last act state, or the time wait state, if the RST bit is set, then enter the closed state, delete the TCP, and return. And again, when a segment arrives and you are in the closing state, third, check the security and precedence. If you are in the SYN receive state and a segment arrives, if the security compartment and precedence in the segment do not exactly match the security compartment and precedence in the TCP, then send a reset and return. If a segment arrives and you're in the established state, the security compartment and precedence in the segment do not exactly match the security compartment and precedence in the TCP, then send a reset. Any outstanding receives and sends should receive reset responses. All segment queues should be flushed. Users should also receive an unsolicited general connection reset signal, and then you should enter the closed state, delete the TCP, and return. Note, this check is placed following the sequence check to prevent a segment from an old connection between these ports with a different security or precedence from causing an abort of the current connection. Upon receiving a segment or the segment event, fourth, check the SYN bit. If you are in the SYN received established state, fin wait state 1, fin wait state 2, or I think it's fin wait 1 state, fin wait 2 state, close wait state, closing state, last act state, time wait state. If the SYN is in the window, it is an error. Send a reset, and any outstanding receives and send should receive reset responses. All segment queues should be flushed. The user should also receive an unsolicited general connection reset signal. Then you should enter the closed state, delete the TCP, and return. If the SYN is not in the window, this step would not be reached, and an ACK would have been sent in the first step. Sequence number check. Fifth, check the ACK field. If the ACK bit is off, drop the segment and return. If the ACK bit is on, if you're in the SYN receive state, if the SYN.unacknowledged number is less than or equal to the segments.acknowledgement number, which is less than or equal to the SYN.next number, then enter the established state and continue processing. If the segment acknowledged is not acceptable, form a reset segment, which would look like the form sequence number equals segment.acknowledgement number, control code equals RST, then send that. If the ACK bit is on, and you're in the established state, if the SYN.unacknowledged is less than the segment.acknowledged number, which is less than or equal to the SYN.next, then set the SYN.unacknowledged number to the segments.acknowledgement number. Any segments on the retransmission queue which are thereby entirely acknowledged are removed. Users should receive positive acknowledgments for buffers which have been sent and fully acknowledged, i.e. the SYN buffer should be returned with an OK response. If the acknowledgement is duplicate, aka when the segment.acknowledgement is less than the SYN.unacknowledged number, it can be ignored. If the acknowledgement acts something not yet SYNed, aka when the SYN.acknowledgement number is greater than the SYN.next number, then send an ACK, drop the segment, and return. And if the SYN.unacknowledgement number is less than the segment.acknowledgement number, which is less than or equal to the SYN.next number, the SYN window should be updated. If the SYN.window L1 is less than the segment.sequence number, or the SYN.window L1 equals the segment.sequence number, and the SYN.WL2 is less than or equal to the segment.acknowledgement number, set the SYN.window to the segments.window, set the SYN.window left, or I'm not sure, the syn.wl1 to the segment.sequence number and set the syn.wl2 to the segment.acknowledgement number. Note that the syn.window is an offset from the syn.unacknowledged. That syn.wl1 records the sequence number of the last segment used to update syn.window, and that syn.wl2 records the acknowledgement number of the last segment used to update syn.window. Then the check here prevents using old segments to update the window. So again, in the event that a segment arrives, this seems like the densest permutation branching like thing. I guess you could call that a tree. So when you get the segment arrives event, if you're in the fin wait 1 state, in addition to the processing for the established state, if our fin is now acknowledged, then enter the fin wait 2 state and continue processing in that state. If you're in the fin wait 2 state, then in addition to processing for the established state, if the retransmission queue is empty, the user's close can be acknowledged, but do not delete the TCP. If you're in the close wait state, do the same processing as for the established state. If you're in the closing state, in addition to the processing for the established state, if the ACK acknowledges our fin, then enter the time wait state. Otherwise, ignore the segment. If you're in the last ACK state, the only thing that can arrive in this state is an acknowledgement of our fin. If our fin is now acknowledged, delete the TCP, enter the closed state, and return. And if you're in the time wait state, the only thing that can arrive in this state is a retransmission of the remote fin. Acknowledge it and restart the 2 MSL timeout. Sixth, check the urge bit. This is again within the event that a segment arrives. You check if there's an urgent bit. If there is an urgent bit and you're in the established state, the fin wait 1 state, or the fin wait 2 state, if the urgent bit is set, store the maximum of the receive.up value or the segment.up value in the receive.up value and signal to the user that the remote side has urgent data if the urgent pointer, aka the receive.up value, is in advance of the data consumed. If the user has already been signaled or is still in the urgent mode for this continuous sequence of urgent data, do not signal the user again. If you are in the close wait state, the closing state, or the last ACK state, or the time wait state, they should not occur since a fin has been received from the remote side and you are ignoring the urgent data. Seventh, if you so the seventh thing that happens if you receive a segment is you process the segment text. If you are in the established state, or the fin wait 1 state, or the fin wait 2 state, once in the established state, it is possible to deliver segment text to user receive buffers. Text from segments can be moved into buffers until either the buffer is full or the segment is empty. If the segment empties and carries a push flag, then the user is informed when the buffer is returned that a push has been received. When the TCP takes responsibility for delivering the data to the user, it must also acknowledge the receipt of the data. Once the TCP takes responsibility for the data, it advances receive.next over the data accepted and adjusts the receive.window as appropriate to the current buffer availability. The total of receive.next and receive.window should not be reduced. Please note the window management suggestions in section 3.7. Send an acknowledgement of the form sequence number equals syn.next, acknowledgement number equals receive.next, control code equals ACK. This acknowledgement should be piggybacked on a segment being transmitted if possible without incurring undue delay. If a segment arrives and you're in the close wait state and the closing state and the last ACK state and the time wait state and you're processing the text, this should not occur since a fin has been received from the remote side. Ignore the segment text. Eighth, if a segment arrives, you check the fin bit. Do not process the fin bit if the state is closed, listen, or syn sent. Since the segment.sequence number cannot be validated, drop the segment and return. If the fin bit is set, signal to the user connection closing and return any pending receives with the same message. Advance the receive.next number over the fin and send an acknowledgement for the fin. Note that the fin implies push for any segment text not yet delivered to the user. If you're in the SYN receive state or the established state, enter the close wait state. If you're in the fin wait 1 state, if our fin has been ACKed, perhaps in this segment, then enter the time wait state. Start the time wait timer, turn off the other timers, otherwise enter the closing state. If you're in the fin wait 2 state, enter the time wait state, start the time wait timer, turn off the other timers. If you're in the close wait state, remain in the close wait state. If you're in the closing state, remain in the closing state. If you're in the last ACK state, remain in the last ACK state. And if you're in the time wait state, remain in the time wait state. Restart the 2 MSL time wait timeout and return. Okay, these are the final events. These ones are in the groups user timeout, user timeout. For any state, if the user timeout expires, flush all queues, signal the user error connection aborted due to user timeout in general. And for any outstanding calls, delete the TCB, enter the closed state, and return. If there's a retransmit timeout event for any state, if the retransmit timeout expires on a segment in the retransmission queue, send the segment at the front of the retransmission queue again, reinitialize the retransmission timer, and return. If there is a time wait timeout, if the time wait timeout expires on a connection, delete the TCB and enter the closed state and return. Oh my goodness, we finally finished this. I'm going to read through the glossary though. This is going to be interesting. 1822, BBN Report 1822, the specification of the interconnection of a host and an IMP. The specification of an interface between a host and the ARPANET. ACK is a control bit of type acknowledge occupying no sequence space, which indicates that the acknowledgement field of this segment specifies the next sequence number the sender of this segment is expecting to receive, hence acknowledging receipt of all previous sequence numbers. ARPANET message, the unit of transmission between a host and an IMP in the ARPANET. The maximum size is about 1012 octets or 8096 bits. ARPANET packet, a unit of transmission used internally in the ARPANET between IMPs. The maximum size is about 126 octets or 1008 bits. Connection, a logical communication path identified by a pair of sockets. Datagram, a message sent in a packet switched computer communications network. Destination address, the destination address, usually the network and host identifiers. FIN is a control bit occupying one sequence number, which indicates that the sender will send no more data or control occupying sequence space. Fragment, a portion of logical unit of data. In particular, an internet fragment is a portion of an internet datagram. FTP is the file transfer protocol. Header is the control information at the beginning of a message, segment, fragment, packet, or block of data. Host is a computer, in particular a source or destination of messages from the point of view of the communication network. Identification is an internet protocol field. This identifying value assigned by the sender aids in assembling the fragments of a datagram. IMP is the interface message processor, the packet switch of the ARPANET. Internet address is a source or destination address specific to the host level. Internet datagram is the unit of data exchange between an internet module and a higher level protocol together with the internet header. IP is the internet protocol. Internet fragment is a portion of the data of an internet datagram with an internet header. IRS is the initial receive sequence number, the first sequence number used by the sender on a connection. ISN is the initial sequence number, the first sequence number used on a connection. It's either the ISS or the IRS. It's selected on a clock-based procedure. The ISS is the initial SYN sequence number, the first sequence number used by the sender on a connection. Man, there's a bunch more stuff here. Well, I'm gonna move through this. I'm gonna skip over the last. I'm exhausted. I'm really hungry. I need to eat some food. But this has been a reading of RFC 793, which is titled Transport Control Protocol, or TCP. It is one of the most ubiquitous programs on the planet, protocols on the planet. any serious computer scientist who wants to write code that exists on the internet, which should be basically every computer scientist, should care a lot about this. This is a super important protocol. I won't pretend that I understood everything there. I try my best here. I'll probably end up having to go through this again at some point in time. And it's been hard. This is the longest one I've done yet. Although, there are some RFCs that are around like 130 pages, like TLS 1.3. That's going to be a hard one to get through. I'm planning on doing that in the future. But it's been a blast. Of course, it's always hard. And I commend anyone who's actually made it through this entire video. I apologize for mispronouncing things or missing some line or something or saying something wrong. It's a long thing, and I just try and get through this stuff without taking too much time to do it at the cost of maybe accuracy or miscomprehension. In any event, if you're interested in more of this type of stuff, just look at some of the other videos on my channel and go ahead to my blog, which is going to have a lot of stuff about this, as well. And I'm going to include some programs too. What I want to do? I want to write some stuff that people can just run, for free. I want to make some open source stuff that people just have, maybe a chat server that people can just host and control all the data, as long as they're, using maybe something like AWS underneath it. Yeah, and I'm going to put a lot of that. Sorry, that was a tangent. I'm going to put a lot of that type of stuff on so that you can, so you can see the exact code and download it, and maybe download Docker containers too, or Docker images. I'm just going to put all that on my website, which is called pieharbor.com. It's pretty simple. It's the same name as this channel, so you probably realize that after you've seen one of my videos or have gotten this far in it. Anyways, thanks for tuning in. And I am so tired, so peace.